So all the attributes go to Intel Labs for this part of the presentation during the submission. There we go. Is this working? So just to give a heads up, so here's our course goals. So we have a great group of speakers here, but I want to give some just highlights of what we're looking to present today. One is to give insights into basically how recent neural models are helping close this gap from between taking what you're reading in research papers today, whether it's at Eurographics or many of the other courses that or conferences that are out there, and closing the gap between what you would see in a research paper, then how would you actually take that into deployment? Well, how would you get that into a rendering engine or into any other tools that you'd like to take that model and deploy it into something that you can then tangibly use? And we'll talk about some of the challenges that we're seeing with data acquisition, which is, we'll hear lots of talks today. I think this morning I was listening to that about looking at data acquisition and the challenges we have there. So we have Sue Joy to talk to that aspect of it. We'll look at development of models, how we're training the models, and how we deploy it. And then looking at that kind of iterative process. Once you have a model, once you have training data, how you determine whether you need more training data, how do you go through that whole process of iteration through that. And then we'll show some practical use cases. Deepak will be showing some cases about the different models that are out there, where we could start, kind of your path forward towards taking neural rendering into production software. So that kind of sets forward our course goals. And to give you the agenda for today, so I'm giving the introduction here, and then Deepak Vimbar will come on and talk about ML for graphics, kind of give you an overview of many different models that you're seeing out there today in research, and kind of ones that are really applicable to the rendering paradigm and content creation. Sujoy will be presenting remotely, so he'll be talking about synthetic data for computer vision, techniques, challenges, and tools that we can use, kind of bridging this sim to real gap, and he's from Unity. And then after that, we'll have I believe, our coffee break at about 3 o'clock. So then we'll come back, and Florent Guinier from Unity Labs will then talk about machine learning in real time, where he'll talk about Barracuda is Unity's framework for how they're delivering that to get a real-time instantiation inferencing of these neural models. And then I'll come back for a conclusion, and then we'll have a QA session where we can open it up and take questions and answers. So some of the areas of exploration in this is what are some of these latest techniques in machine learning for rendering? So we'll break down, are we looking at, kind of UNets or GAN-based approaches? What types of models have shown those promising results? While I was at Intel, we looked at Open Image Denoiser, which was integrated into Blender and several other packages. So that was an area that we did some discovery. What kind of data to train these models? So is that data something that we can look at that's highly easy to get, whether they're open source data sets or whether we have to curate that data ourselves and render that data? And then how practically is it to deploy the models? So those are kind of the areas that we're going to talk about through this course, and the different speakers will speak to each of these different areas. Now, some of the challenges that we look at when we think about how do we take these models and deploy them and get a research paper to that, we have to kind of set off and think about the different aspects. One is are we looking at for this in real time? Do we need 30 frames a second, 60 frames, 90 frames a second if we're looking at like a head-mounted display or something? Versus offline, do we have a lot of time to compute highly photorealistic type of neural models and inference in seconds or other times? So there's trade-offs that we have to think, and there's always this tension between performance versus quality, and thinking about how to tune our hyperparameters, how many layers of our models do we have, and looking at, can we use a UNet-based approach, or do we use a GAN that may be harder to train, and different aspects. And then tuning to the hardware. Do we want to go through and go all the way down to look at quantization layers? Do we want to do specific coding for a particular architecture? So these are kind of the challenges that we think about when we're looking at whether it's real-time versus offline. Now, data acquisition, it's always been a challenging aspect. One is the data sets available? I mean, you get lots of different data sets. Some you may have persons that you can go download. Some you may have certain scenes. Some are just a car. So there's lots of different data sets, but is it the right data set you need? Do you have all the buffers, auxiliary buffers, and other things that you need to train your models? And if you have to curate your own data sets, do you have the 3D models that allow you to do that? So those are things that you have to think about when looking at this. And if you do have the 3D assets, then you have to export all those models, whether you're using Unity to go say, hey, I want normals, I want albedo, I want motion vectors, or other aspects. And then, can I take some real-world examples, or am I just looking at using synthetic data, or a mixture of the two? And Sujoy will be talking into that area. And then if we move into deployment, thinking about, do I have a model, whether it's in PyTorch or TensorFlow, can I export that to Onyx and then use an Onyx runtime for that? Or can I use Unity Barracuda that Florent will talk about? And in that case, am I looking for a single frame rendering or integrate into a game engine? Maybe I wanted to go through a compute shader. So there's many different ways to think about this. And even if you're going to hand tuning or using the API, like you could use something like DirectML, but then you have a very lower level API for some of these cases. Some of the other challenges is looking at these different rendering attributes, such as the input buffers. How many input buffers, what types of input buffers do I need? Is it a series of G buffers? Is it depth maps? Do I need motion vectors? Do I need optical flow? So those are many different things. Maybe you're doing some ablation state. Maybe you use lots of input buffers, and then you use ablation states to determine which ones you can kind of call out. Resolution changes. So are we thinking about 540, 1080, 4K resolutions? Do I have to have different models for each of these? Is it agnostic to the resolution changes that the upscaler can handle that? These are all things that we need to think about when looking at your models. And then one aspect we were looking at is temporal stability as well. So if we look at frame-to-frame coherence, that's one thing that's very important as you're looking through these 3D scenes. You don't want a lot of popping, a lot of artifacts. So how do you control that? And we'll talk a little bit about that. And then there's been some talks today looking at HDR and LDR type lighting. Do we use tone mapping? Do we train HDR? Do we convert it tone map to LDR and then go back? So those are some of the approaches. And just a few other things to think about is the reproducibility of these models, the robustness, and what are your quality comparison metrics. If it's, is it a highly ray traced thing, you're looking at SSIM or PSNR, or if it's a style transfer, is it a perceptual quality? So there's different ways to think about quality comparisons in this case. Now, if we think about looking at when you're crafting, here's what I want, my goal in mind of some form or project I want to get started. So you want to define these goals. What is your desired output? If it's like a super resolution model, you want to take a low res model and output a high res model of that and get really high quality. So you want to think about how these goals, you want to think about what is the performance that you need? What's the quality that you can, is acceptable for these models? Do you need more training data, higher reses? And then what's your criteria for success when you deployed this? So basically listening through your goals, and once you go through that, then thinking about the model development. So there's lots of models out there that you can use, like VGG, other types of models. Can you take an existing model, or do you need to create your own model in this case? And defining your inputs, outputs, looking at the different model architectures, whether it's a variational autoencoder, a GAN, a multi-layer perceptron, and the NERF-based models you're seeing today. So really thinking about which architecture would fit and can work in your different areas. And then thinking about some of the loss functions, whether it's L1, L2, or perceptual loss, or a combination of many different loss functions. Those are other areas to think about in your model development. And that seems where a lot of the innovation is happening in the loss functions. And then acquiring your training data so that you can train these models. We already mentioned the public data sets, but obviously some of the real versus synthetic. The synthetic you get to create, but you have to spend a lot of time in exporting all that data and getting the 3D models for that. And then going into training and deployment. So we'll train and deployment. Is training time an issue? Do you have weeks? Do you have hours? Do you have minutes? It really depends on your different aspects when you think about that. And then iterating and testing, iterating, going through that process. And then deploying it, whether it's Onyx runtime, as we said, or Unity, or Barracuda, or DirectML. And then optimizing, do I want to quantize to 16-bit, to 8-bit, or even 4-bit, thinking about these different aspects. But this is kind of a very high-level picture of a workflow for practical machine learning. So just give a few different examples that when I was at Intel looking at it. One, we were looking at the super resolution. Here's a image credit from Meta's research, and basically taking lower resolution output and then be able to upscale that to a higher resolution. And you could take in motion vectors or pass frames or other data to upscale it. So that's one to think about kind of on the post-processing. Similarly, a couple others in that same case could be whether it's frame extrapolation, taking some prior frames, run it through a UNet, and then can you predict the future frame? So that's another area of research we're looking at. And then style transfer. So this is a case where you want to basically change the concept of what the style looks like of your end buffer. And I'll show you. That one we'll dive a little bit deeper in the next couple of slides. So if we walk through kind of that simplified workflow model, if we took style transfer as an object, so some of our goals here were kind of real time for videos and 3D graphic scenes. That's what we set off to start with. We said we wanted temporally consistent. We wanted high definition resolution, so 1080 to 4K was kind of our targets. We also wanted the ability to segment out objects. So we wanted to be able to personalize the style transfer. So if I was a celebrity on Twitch and I want a very particular style, could I apply that style to an object in that scene and not the entire frame? And then we were looking at trade-offs. Okay, testing there. So on the trade-offs, we were looking at training for a particular style. So do we have to have changing weights for each model and each different style that we want? So if we have 5 styles, we need to retrain the model 5 times. Or do we have something like a universal style transfer where you could change between many different styles, but sometimes it doesn't have the same quality that you get on per style basis. And then the temporal stability, there's one aspect that can you train the model using optical flow on training time, or do I have input buffers such as motion vectors that I can use at inference time? So these are some of the trade-offs we were making. We eventually at the time were choosing training per style, and we were also at the time training at the temporal stability at training time. Now, if we're going through some other aspects, I was looking at the data acquisition. So if I look at the data acquisition and model development, so we chose for the data acquisition side for style transfer, we were grabbing the Flying Things 3D and Monka data sets, which had optical flow and motion boundaries, so that was a pretty good aspect. Like I said, we wanted to do character segmentation, so we grabbed some data sets for Coco, the supervisedly person data set, and Carvana, because we were looking at using some videos of like a race car game in that case, so we would segment out the cars in that point. And then for model development, we were looking at, there's lots of different models out there. I mean, it's a huge research space. So we actually went and explored that. RicoNet was one that we started off with, had a really good performance characteristics with some temporal stability. And we were looking at modifying that, but also maybe adding parts of that to other models. And then adding this ability of per object style transfer. So that's kind of the different aspects we were looking at when doing the data acquisition or the model development. And here's some results that we had achieved. This is the Viking data set from Unity, and this is so the left-hand side there is a 3D asset rendered in Unity. The right side is a video that we were showing. And that's kind of the results we were getting from the models that we were showing and be able to inference in real time. And then if we move on to the next one, this is where we're looking at segmenting and applying different styles to different characters or different people. So the left-hand side, you see the male and female have different styles, and then if you go on the right-hand side, we even applied a different style to the background as well. So with that, I'll conclude the introduction, and I'll turn it over to Deepak Vimbar. So again, we'll go through the presentations, and then we'll have a Q&A at the end of the course.
Okay. Thanks, Carl. So my name is Deepak Vimbar. I'm a research scientist in Intel Labs doing graphics research. And today I'm going to present a brief overview of some of the techniques that we've seen deployed, some of the challenges. Carl spoke quite well about some of the style transfer work we did. I'll tell you a little bit more about the challenges that we're currently facing and some of the solutions we're coming up with. This is just the general agenda. I'll speak a little bit about machine learning and graphics. I think a lot of the folks here in this room have actually done some work integrating this or doing work. Show of hands, how many people are doing machine learning for graphics? So maybe about 40% of the people. How many people do academic research versus deployment into solutions? Academic research? Okay. Deployment and solutions? Okay. I think this is good because I think one of the things we want to kind of present as some of the challenges in actually taking academic research and deploying this into a product that can actually be sent over to people or with traditional ISVs. So this is good. I mean, a lot of the work is kind of focused on the entire spectrum of the graphics pipeline, all the way from content creation to special effects like cinematic quality videos, denoisers, for example. And a lot of the focus is also on improving rendering, especially for like VR or AR or real-time, like 60 frames a second graphics at high resolutions. And if you kind of think about it, at 4K resolution screen and you're doing 60 frames a second, you only have 16 milliseconds to render a frame. So how would you actually do this in a fixed time? And some of the things that we did essentially gives you a little bit more leeway to say, I'm going to give you 32 milliseconds to render a frame, which is the frame extrapolation work, or anything that's kind of taking too much time in the rendering pipeline. You try to offload it into a machine learning-based approach, which is some of the post-processing effects, and try to come up with a network that can do all these things in maybe one Uber network. That's the augmenting rendering aspect of it, and then we'll kind of speak about some of the challenges and the opportunities that we envision going forward. So everyone knows that there's increased machine learning and computer graphics across the whole spectrum, whether it's democratizing content creation, it's offline rendering, you want to get the best quality, but you don't have like 2 days to render a frame, or even like real-time gaming at high resolutions. And the main idea here is either you're improving the quality, so you have limited resources and you want to get the best quality possible, or you're reducing the power it requires to render a frame. So you render a low-res frame and you upsample it using a traditional graphics technique or a machine learning-based technique. And the idea here is either you're reducing the authoring time, you're reducing the rendering time, or you're giving a better quality at the same power envelopes, and across like a client instantiation or client-cloud instantiation for like cloud gaming. A lot of the techniques are kind of focused on GPUs, CPUs, or TPUs. You want to have a good enough ecosystem and software to make this all possible. And again, like Carl said, you have challenges with data sets. Not many data sets are available, unlike computer vision. Some of the data sets we render are in the terabytes to train, and they can't easily kind of transport them across, so it's not really easy to share them. The models are usually proprietary, so you take a published model and maybe do some tweaks internally with the data that you have. And then the biggest thing is going to be, what is your target platform you're deploying this on? I mean, you need to be very, very cognizant of that, and you need to be thinking about the power and the time budget that you have. And generalization is somewhat important, but for games, I think it's okay if it doesn't generalize well, but if you're an IHV, independent hardware vendor, you don't want to retrain for every game, so you maybe want to fine-tune on a per-game basis. And we'll kind of get into that a little bit. This is just a quick representation. The one thing I want to kind of make clear here is that the data set generation compared to computer vision is a little bit more easier. Unlike computer vision, where you're acquiring data sets, you can always go and re-render data sets. If you decided that you want an albedo buffer or you need a depth map, you can go re-render them with the data set that you have. But again, it takes time, so there's a trade-off there. The neural network, I mean, pick one that gives you the characteristics, and there are a lot of work out there. We won't kind of get into the details of it. And how do you kind of integrate this into the rendering pipeline? That becomes more important. Obviously, a lot of the work is essentially PyTorch or TensorFlow. In a rendering pipeline which uses DirectX or Vulkan, you can't kind of context switch between the two of them because that's going to kill any performance. Even if you're not context switching, whether you're using compute shaders or you have highly efficient kernels that are fused and implemented, targeting your hardware becomes more important. And then obviously you get the result at the end of it, and then hopefully the result is decent enough. Some examples of this, we won't kind of get into all the examples. Synthetic face generation, I think that's always interesting. Animation, animation becomes more interesting with the whole notion of the metaverse and representing people in virtual worlds. How do you capture people? How do you represent them? And we'll kind of get into a little bit more detail about this. GauGAN is an example of taking something semantically simple and trying to create photorealistic images. So it's almost like paint and then getting better quality photorealistic images at the back end of it. For rendering, the two things I want to kind of point out here is open image denoise, which is on the top left-hand corner. The idea here is cinematic quality content, but you don't want to render at 32K samples per pixel. You want to render maybe 16 or 32 samples per pixel, denoise it, and get similar quality to 32K samples per pixel. And the similar thing with the DL super sampling. You want to render a smaller buffer and then use deep learning-based methods to upsample it to 4K techniques, so you're saving on rendering costs. We'll speak a little bit about content generation with a specific use case about representing avatars. We'll kind of get into the neural animation. How do you have people kind of walk around using neural network techniques? How do you have codec avatars? The notion of representing facial expression, avatar motion in a virtual world. Kind of thinking about it, I've worked in VR for quite a long time. If you want to represent people in VR, you need to either have a motion capture suit with like multiple markers in your body, or you have egocentric cameras capturing yourself, and then you're kind of representing them. And this becomes cumbersome, especially if you're just trying to represent yourself to your player in a VR world. And the same thing with facial animations. To get really good quality facial animations in the past, you needed to have like multiple cameras looking at your face and good lighting and kind of try to project this back. And again, there were still issues with it. You had to kind of go tweak the training data sets. You had to tweak how the facial animations were working. And it still didn't really look realistic. And it required a lot of expertise to make this happen. One thing that kind of came out maybe about 5 years ago is this really small network called face function neural network, in which they were trying to look at human animation, bipedal animation, over varying terrain. And they used like a simple 3-level network to make this possible. So they took motion capture data, which was captured and cleaned up, and they essentially fit it to the different terrains. So they had people like walk over tables, walk over boxes, jog, run, and they used this training data to essentially come up with a model that essentially simulated, given unknown environment like terrain, have a person click and say, I want to go to this place, and then the neural network essentially captures and computes the steps that it needs to take. And prior to this, a lot of it was essentially done using keyframe animation, and the input that the network essentially takes is the user input, whether you're going in front, you're going in the back, and the scene geometry, so how high is the displacement from where you are today. And obviously the face function, the face function is like whether you're moving your leg up, leg down, is your knee bent, and so on. And this was integrated into Ubisoft's games. The performance is really, really fast. Again, it's a 3-level network. I think it was about 2 to 3 milliseconds to compute everything. So this is an example of, if you want to have a person kind of walk through in a virtual world, you don't need all the control, you don't need to know and have intersections with the geometry. You can train a simple neural network to essentially overcome some of the limitations of this. The second thing, which is really interesting, is the notion of social representation of faces in virtual reality. Unlike like face-to-face communication and even Zoom calls, you have some latency in actually seeing what's going on. And this becomes even more prevalent when you have like a head-mounted display that's blocking your eyes. If the person can't see your eyes, you don't really know if you're looking at the person, you're looking at something else. So what Facebook and Meta Reality Labs did is essentially augmented your head-mounted display with like multiple sensors. So both cameras looking at the eye, looking down at your chin. And then the idea here is if you're having telepresence between two distributed participants, you want to be able to present like you're face-to-face, and that's a really good goal to have. So essentially social interaction with multiple users. So what they did is they took essentially two VAEs. The first thing on the top left-hand side you'll see is they took a light state capture of a person's face on multiple different angles with known lighting conditions. And they developed a VAE to essentially transfer that into latent encoding, which is this Z. And they use this latent encoding in the view-dependent vector to essentially do a view-dependent rendering. And you'll kind of see the ground truth, which is on the left-hand side, and the rendered view, which is on the right-hand side. The other thing also to note here is to kind of map what the facial animations are to the actual camera, they developed like a synthetic version of the face with the exact parameters of the camera itself. So you're capturing not only the camera in the real world, but it can also synthetically capture like a fake camera and kind of map that similarly using the VAE. And they also used a GAN network to essentially figure out if there was any difference between the synthetic generated faces and the actual captured faces. And once you kind of got to that, there was no difference. The left-hand side also kind of shows the different camera placements. You had two cameras right near the lens looking down at the eyes, and then one camera on the nose bridge kind of looking down at your face and mouth to capture your expressions going forward. And this is the paper from Lombardi. And again, this is just like a talking head avatar. They have done kind of more work with this, with the whole body representation, and I'm sure there's more work coming out at SIGGRAPH, looking at other aspects of this, including relighting. And again, this looks pretty believable. This is like the earlier instantiation of it. The thing that you want to kind of do also is have like hair or facial motion, relighting, any kind of occlusion effects like sunglasses and so on. The other aspect I want to kind of speak about is there's been a lot of work done on semantic image-to-image translation. So given like a simplistic image, you'll kind of see that from the data set, the auto-driving data set. You take a simple segmented image of cars, roads, trees, and so on, and you can essentially generate a photorealistic image. And not only image, but also videos, right? And you can use this for synthetic training. The notion here is you're augmenting what you're capturing from the real world with synthetic data to simulate like the tree falling down on the road. So what do you do when you're driving the autonomous car? And an extension of this to essentially democratize content creation is NERF, neural radiance fields, where you can take like monocular multi-camera view images, or you can take a camera and kind of walk around this object, in this case, Lego, and then essentially generate synthetic novel views of the scene, essentially view synthesis. And using, unlike CNNs, they're using MLPs to do this, so many small networks to make this happen. And one of the advantages of this is everyone has a cell phone, so if you want to kind of capture something from multiple views, instead of using photogrammetry, you can just take multiple photographs or even like a 360 video of it and create a full 3D avatar that can be imported into any virtual world, Blender, Unity, and so on. The initial limitations of this was it took a really long time to train, but recently Muller et al. Published a lot of work on essentially fast neurographics primitives training. So from acquisition to training is less than 4 seconds, and of course you can kind of train them for more time. You can train them, but also separate out appearance, lighting, textures from the models. Some of the work that is coming out right now is kind of looking at not only static images, but dynamic objects. So if an object is moving, how do you capture it? And essentially city-scale objects. I mean, there's like BlockNerve, which does like drive through of San Francisco. So a lot of this is kind of moving away from having specialized skills in 3D modeling software to democratizing someone with a cell phone or even like a simple setup to be able to capture all this, change the different parameters and import them and sell them in different packages and APIs. So we saw a little bit about ML for content creation. In this section, we'll speak a little bit about ML for rendering. So how would you improve the image quality? How would you improve the rendering time or the speed? Or how would you reduce the power consumption required to make this happen? One of the earliest paper was by Nalbach at Eurographics, the deep shading paper. They realized that a lot of the post-processing effects, essentially learned heuristic effects, could be replaced by using like a learned machine learning model. They use CNNs for this. And again, similar to what we said about computer graphics and having access to all the different G-buffer information, you can feed all these, again, assuming it's differentiable, you can feed all this into a network which approximates, based on the loss functions and so on, the output that you desire. And you can kind of tweak this based on what you're doing. So this was the first application of a U-shaped CNN. They used the input buffers like albedo, normal maps, depth maps, and motion vectors to essentially synthesize effects such as ambient occlusion, depth of field, motion blur. And the interesting thing about this was you could also combine multiple effects like AA and AO into one network. And again, the resolution of this at that time was pretty small. I think it was like 256 by 256. But again, it's a CNN. It can be applied to a higher resolution image. And there's been more work done on this to improve the performance. Carl spoke about segmented style transfer. I think unlike the full frame style transfer that Florent is going to speak about, one of the things that we were kind of looking at is this, the notion of I want to apply this effect only to a part of the frame. In this example, we are applying this only on the tennis player in the foreground, and you can kind of swap between the different effects. The challenges we faced with this is the application of the style depends upon the mask itself. So you're kind of extracting out the mask of the user itself. And for video content, it's a little bit harder because you're running maybe a network to get it, and then you're propagating that rather than trying to detect a mask every time. And it becomes a little bit more easier with the 3D rendered content. So this is on the bottom right-hand side. The tiger itself is synthetically generated, so we have pixel-precise depth maps which help us to only apply it to the tiger as opposed to the background. And you can replace the background and so on. And one of the things that we can do with this is essentially replace your zoom backgrounds with style transfer backgrounds maybe, or maybe put like a Van Gogh effect on yourself when you're having a boring Teams meeting. I don't know. And again, the challenges in gaming is kind of focused on we want to have the best quality at high resolution, and you want to have maybe 60, or in case of VR, 90, 120 frames per second. And if you're kind of doing this all on the single client or a single head-mounted display, the compute that you have there are going to be some bottlenecks in texture sizes. You cannot have like multiple gigabytes of textures. Your models cannot be highly detailed, so the level of tessellation is going to be much smaller. And we want to be able to maybe somehow shrink it, but not at the cost of quality itself. And one of the things we're kind of seeing is with hybrid rendering is rasterization plus ray tracing or path tracing becoming more prevalent. We want to have things like global illumination or ray trace shadows or perfect caustics all in a game to improve the realism of it, but you're fixed in your time budget of 16 or less than 10 milliseconds to make this all happen. Like they say, I mean, you can increase the amount of compute that you have, but the artists are always going to find ways to kind of fill up the time, extra time that you give them. So, and again, that's a good thing. And the challenge for us as developers is to enable these photorealistic effects in games and other content to make possible. So one of the first things that NVIDIA did, this was back in like 2018, was deep learning supersampling, which is you render, rather than rendering a 4K buffer as an image, you render maybe a 1080p image or a 720p image, and you upsample it using a deep learning-based method. And what this kind of gives you is you can still render all the effects at low resolution within the time budget, and you have fixed cost inference to upsample it into a 4K image. And again, it gives you a tremendous amount of increase in frame rate. So if you're rendering a 4K image and you're only rendering at 20 frames a second, maybe using a deep learning-based method, you get to 35 frames a second, which is still eminently playable as opposed to 20 frames a second. And again, the details, maybe I'm not really privy to it, but what I can understand is they're using multiple 1080p images along with the motion vectors and using a convolutional autoencoder to essentially have the 4K output. And compared to like a ground truth 16 sample per pixel, it still looks pretty good. And this is the one thing that I want to kind of focus on. So when we kind of look at a lot of the papers and we kind of look at like side-by-side image comparison at full resolution, we always find like noisy regions that are a pixel or two off, or the PSNR numbers are off a little bit. But I think the main focus for us is going to be, is it playable? Are the people actually going to perceive any difference if that 1 or 2 pixels are off? And that is something that is really, really hard unless there's like more research done or there is more like an automated tool that is available that says, for this 4K image, those 10% of the pixels that were off, it didn't really make a difference because they were at the periphery of the image. If the people don't really focus on it, if you're playing like a FPS, all you care about is where the missile trail is coming from, what's in front of you, and where the explosions are happening. So if that little thing at the background is off, that's fine. I mean, people are not going to notice a difference. At least some of the studies that we have done, you can change a whole bunch of pixels as long as they're not focused, and people are not going to notice the difference. And this becomes even more critical when we're kind of doing work in neural frame extrapolation, which is essentially predicting a whole new frame using neural networks as opposed to rendering a frame. We spent a lot of time trying to kind of figure out, are those pixels correct? But ultimately, we realized that it's off at the border, so people are not really going to see it as long as it doesn't flicker from one frame to the next frame. So coming back to DLSS, again, it renders a low-resolution image and samples it. And again, this has wide adoption in most games. Unreal and Unity have this implemented. And the interesting thing about this is you're not doing this as a part of the rendering pipeline. You're doing this using the tensor cores. So you're doing asynchronous compute when you're still doing the rendering. And that gives you the best performance. Similarly, Intel put out OpenImage denoise. This is to denoise. It's a denoising library for ray-traced images, or path-traced images. It's been integrated with Blender. And it can also be used to denoise the final frames as well as bake light maps. And the idea here is you want to have the best quality for cinematic rendering. Traditionally, a final frame is done at really high sample per pixel. But you don't want to spend like 2 hours, 3 hours trying to render a single frame. So maybe you render only 16 samples per pixel or 32 samples per pixels, run through a denoising network, and it kind of gives you similar quality to it. And we have some examples of it further on. It is suitable for interactive, that's work that's still ongoing, as well as offline rendering. It has a simple C, C++ API. It can be integrated into rendering applications, and it's available at that link, openimagedenoise.org. Attila, who is the lead developer of it, he was there during SIGGRAPH, but if you want to get in touch with him, just shoot. There should be contacts there, or just send me an email, and I can put you in touch with him. So this is an example. I mean, you can kind of see some of the a really good light transport effects that you see, like depth of field and really high lighting effects. And this is rendered, I think, at 32K kilosamples per pixel using Blender. And the idea here is we want to get the quality that is on the left-hand side, but you only want to render 16 sample per pixel as on the right-hand side. And this becomes more interesting as more and more hardware vendors start putting ray tracing support into the GPUs. So you want to maybe use the limited ray tracing compute that you have to still give the best quality for gaming applications. For non-interactive applications, I think it's more of a fungible target, but you cannot render 32K samples per pixel at 60 frames a second today. But 16 samples per pixel may still be possible, and use a denoising to kind of get similar quality as the left-hand side. So that's the goal of using these denoising techniques. So as a part of this, I want to kind of say that this is just kind of scratching the surface of some applications. Some of the more recent papers show a lot more promise. I mean, almost every SIGGRAPH and every 3 to 4 months, there's a new nerf-based paper or a new, multi-view stereo-based paper that improves performance. And it's going to only steadily increase going forward. I mean, there's a whole bunch of work that still needs to be done, like relighting. What happens if the artist decides that that's not the right light for a nerf-based model? You can't say, okay, go generate me, 100 more data set. He's like, at that point, I'll just generate it myself. I mean, why would I tell you to go use a deep learning model to do it? And applications from metaverse to ray tracing to path tracing, and again, improving photorealism in games. There's a lot of work out there. I have maybe scratched 0.01% of it, but I'm sure there's going to be papers at Eurographics that push the state-of-the-art forward, as well as SIGGRAPH that push it forward. The thing that I want to kind of focus the last part of the talk is just on challenges. I mean, it's great to get publications at conferences, and it's good to put out data sets and networks, but the challenge is always going to be, how are we going to deploy this? Is it going to work for your data set? Is it going to work in the time budget that you have? Is it going to work across all the different kinds of usages that you want, from an FPS game to a strategy game and so on? And I'm not saying that we have solved all the problems. I think this is just something to kind of think about as we develop these techniques. And again, there becomes like a difference between the research to applied research to advanced pathfinding to early productization to actual deployment. But just kind of thinking about the whole ecosystem sometimes kind of gives you a better perspective on things. Again, so the way that we usually operate is we take published neural networks, or we develop neural networks in-house. We generate additional training data, and this training data is sometimes hard to kind of come by. Usually for graphics, depending on whether they're open sourcing the data set or not, replicating the data becomes an issue. And again, you get the data set if it's available, or you generate the data set internally, and then based on the application, you generate even more data set. I don't think you can have enough data, and we kind of routinely run into multiple terabytes of data that we actually need to make this happen. I'm sure it's a problem in computer vision too, but it just becomes an exponential problem in computer graphics. You come up with a network, you train it with the thing, and that takes about 5 days, 10 days, I don't know, however long it takes. And then you're happy with the performance, and you kind of go through this. You optimize it, to quantize, prune, whatever you want to do, and then you test and deploy it. And you kind of go through this multiple times, and we have examples of from the first instantiation to actual deployment is about 10 months, maybe longer, depending upon which aspect you're trying to do. And a lot of it is iterative. There's always going to be something that has improved, a new loss function that came up, or a new filter that came up, or a new CNN that came up. And ultimately, the goal is to deploy this at scale. From the data set aspect itself, commonly we generate multiple different types of data. We don't really know what kind of data we need because we don't want to go back and generate the data set. We usually share like artist time with like other people. Either we do the data set ourselves or we kind of offload it to someone else who's kind of more skilled in generating the data set for us. And every kind of data imaginable, albedo, specular highlights, normal maps, depth maps, it's just there. I mean, you choose to use it, you choose not to use it, that's okay. Most of the data can be directly got from game engines, Blender, Unity, Unreal. You may have to write your own custom shader to get some esoteric data, but that's pretty simple. And it's easier for us to go from like 4K data set. You can always downsample it if needed. But rendering a 4K data set takes a really long time. And again, we are going more into 4K, 8K data sets. And it takes a really long time to do that. So again, some considerations for it. It's a trade-off between training time and quality. The more data that you have, it's going to be better. But at some point, there's going to be incrementally less. So maybe the first 1,000 images get you the best quality, and the next 1,000 images don't, and that's okay. Licensing of data sets, that's a big issue. A lot of the data sets that maybe we use internally, just because we work with ISVs and like custom animation studios, we cannot open source the data set. It's not our property. So there's a lack of like open source data sets. And it's changing, definitely, but I think it has to change faster. Generalizability is less of a problem for us. We tend to kind of focus on one or two things immediately. I think we need to kind of improve that, but right now I'm okay with that. And again, data formats and whether you're using EXRs or PNGs, I think that's all something to think about. And the reason I say EXR versus PNG is frame extrapolation. If you're doing something in the cloud and trying to transmit data to the client, and we were doing this for predicting a frame in case of frame drops at the client to improve cloud gaming. If you're dropping a frame that is highly compressed, that's being sent because of network latencies, adding more EXR data sets or uncompressed buffers to it is not going to improve the performance in any way. You can't send those buffers. So just kind of thinking about how it's going to be deployed becomes more of a challenge at the beginning. So if you say we want to do frame extrapolation from client to cloud, then you're kind of bounded by the problem of I cannot add more data buffers. So what can I compute locally at the cloud or compute locally in transit or compute at the client so it doesn't add to the latency and so on. So that's something to kind of think about. Again, neural network architecture and performance, similar to academic research, where it kind of builds upon prior published research. It takes some effort to modify it to what you want it to do. There are lots of good tools out there, TensorRT, OpenVINO, that let you take a network and kind of pass it through like a network optimizer and spit out like a optimized network. And most of them take like an ONNX file as input. The thing to kind of focus on here is it depends on which version of ONNX. They have different levels and so on. So just be aware of it. Usually looking at the product notes will help you. And again, a lot of the work is kind of done, at least in the past, on images, like style transfer was on images. But transferring images to a sequence of images or videos is always going to be interesting. And the goal here is to decrease the temporal artifacts, especially around the edges or flickering artifacts where a section of the screen lights up, because the human visual system is really, really perceptive to changes in brilliance and light intensity and so on. Deployment, I think this is really, really critical. You need to kind of think about how you're deploying this. If you're doing this in an offline renderer, then maybe doing that extra call to PyTorch or TensorFlow is okay. But if you're doing this as a part of the rendering pipeline, and I know Florent is going to speak about Barracuda, the transferring from graphics context to a compute context is going to kill any performance. And even in the compute context, depending on how optimized your compute pipeline is, whether it's asynchronous, it's fully integrated, you need to do mem copies. All these kind of play a role in the performance that you get. And even whether you're doing this to the metal, do you have the right drivers to make this? And that's why you kind of see a lot of variability in the performance itself. Similar to the Wild West of graphics a long time ago, and then the standardization with DirectX and Vulkan and OpenGL, there is more acknowledgement of compute, as in deep learning compute, as a part of the graphics pipeline. So you see things like Windows ML, DirectML starting to evolve. That kind of reduces some of the programmer burden to make this all happen. And both Unity and Unreal do have support now to integrate like Onyx networks or Onyx models directly as a part of the rendering pipeline. And this is really, really good. So then you can kind of look at the deployment itself. You don't have to worry too much about how to set it up, and you let Unity and Unreal take care of that for you. You just call maybe 3 or 4 lines, and it loads the Onyx file that has been optimized, and you can get the performance that you need. So to conclude, it's a really exciting time to be in graphics. I think similar to how computer vision was changed with the integration of machine learning and deep learning. We are seeing that happen. I mean, even from 2016 to now, it used to be like 1 or 2 papers at SIGGRAPH. Now it's like 1 or 2 papers using non-deep learning based techniques. And people usually say at the beginning of the thing, this is one of the papers that is not using deep learning. And it's like, wow, how did you do this? And that's great. I think that's really, really nice. And again, the focus is on improving quality, reducing power, or improving performance, or making it easy for people to make all this happen. We are seeing improved hardware as well as system support, both from the hardware vendors as well as the software vendors. And generally, if a feature is not available, you can always file a bug, and people will go and make this happen in the next iteration of the API. And there are always challenges, data sets, networks, deployments. But Intel Graphics is hiring. We do have a graphics research organization. I can put you in touch with the people. Just meet me after or send me an email. My email's on the beginning of the slides. Thank you so much. With this, we'll go to Sujal.
Hello. Can everybody see and hear me? Not sure. Hopefully. Let's now try sharing the screen and see how that goes. And again, hopefully people can. Oh, I didn't look. Okay. Not sure if people are able to see and hear my screen right now. Is that? Carl or Deepak or Florence, can you, I don't know if it's possible for you to confirm in the chat whether or not people can see things.
Hi, Sujoy. So we could hear you. We could see the slides coming up. So you should be
good. Very good. Sorry. I was just like,
full screen or no?
All right. Thank you. Thank you.
All right. Trying to see if we can get the slides in full screen.
Yes.
There we go.
How about now?
Okay, sounds good. Go
All
ahead.
right, fantastic. Thank you. I was just like, I'm not sure if it's full screen showing up or anything's happening. Okay, hopefully everybody can hear and see me. So as Deepak said, so I'm Sujoy. I'm one of the 2 presenters from Unity. And I'll be presenting on how we can use all these incredible innovations that come out of the graphics community to help drive what we might call more traditional computer vision applications. So this is about using synthetic data for computer vision and the techniques that are available to us and the challenges and maybe the tools that we're able to provide the community to try to advance this problem. Okay, so I know I'm between everybody and their coffee break, so I'll try to go quickly here. But in the talk, I'll give a brief introduction to sort of the challenges in computer vision around data, the advantages synthetic data have, then the methods that we can use to apply synthetic data to real computer vision problems, the burdens that these methods then put on our graphic systems and our content, and then talk about some benchmark case studies that we've done, one in particular on human-centric computer vision, that we hope to help advance the community's research in this area. Okay, so computer vision over the last 10 years, almost 8 years maybe, has really seen an explosion due to the advent of deep learning methods and neural networks, in convolutional neural networks in particular in computer vision. And that has driven advancements in a number of fields. So in autonomous vehicles, right, we've all still talking about autonomous vehicles where we're detecting objects, lane marking, signs, traffic signals. In robotics, where they're trying to use the robotic sensing systems, understanding their environments to safely interact with humans and recognize products or components that need to be manipulated. In retail, you're seeing cashiers, checkouts, inventory management systems, and other kinds of analytics. And in security, of course, the need to identify potential threats. In all of these fields, there is a need for labeled data. In fact, there's a need for massive amounts of labeled data in order to drive these computer vision applications. So the challenge there is that real world data is tricky, right? It's expensive to acquire and label, is time consuming to acquire and label. It is, because of that, it can often be biased or insufficient, by which we mean you may have acquired data in a specific domain that is slightly shifted from your target domain. So for example, you acquired all your self-driving car data in San Francisco, but you'd like to deploy your system in Phoenix. This is maybe not the largest domain shift you can experience in the world, but still enough to cause problems. And often also, particularly when we're thinking about human-centric computer vision problems, there is a privacy and compliance concern with the data that's being acquired. I mean, in typical computer vision workflow, you acquire those real-world images, then label and annotate them. You then train a computer vision model. You then evaluate the computer vision model on hopefully some test set or some higher level business metrics that you're trying to understand. And then you deploy that model to production. And often you are iterating on your system. After evaluation, you realize I don't have enough data or the right kind of data. You have to reacquire data, relabel, retrain your model. Sometimes even at deployment time, you realize, because your true test set, as they say, is the real world, and you realize, oh no, I'm having all these error modes show up. I need to now go reacquire the data. And this part of your process can be about 70% of your time in developing a computer vision based application is actually sitting here in the collecting and annotating of data. Now, one thing to keep in mind is that percentage can actually climb depending on the complexity of tasks you're trying to solve with computer vision. So if we think about something as simple as this little example scene that you can find in sort of almost every data set of sort of a street, and you're trying to build a computer vision application, and maybe you're starting with saying, hey, I just need to build a car detector. And you say, okay, great. I'll just put bounding boxes on all the cars. And you can even see in this example, which is from a real data set, one of the cars is maybe not even put a bounding box on. Nobody's really sure. Should you put a bounding box in that car in the corner? But you put bounding boxes on the cars. And then you realize, that's not quite giving me everything I need to know about the scene. I really need to know where every pixel of every car is, and every person, and every street, and so forth. And you might semantically segment the system. And that requires you to relabel all your data, which is quite expensive. You can imagine this kind of labeling is very expensive, particularly if it's human-based. Even if it's assisted by other computer vision systems, it is still, or technology assisted, it's still very time consuming. You may then realize that's even not really enough. I need to know where every pixel of every instance of every class is. And so then you would call it instance segmentation. So here you can see in this corner, every car is now labeled with a bounding box and a unique color. Every person has a bounding box and a unique color. And then you can combine these semantic and instance level segmentations into what's called panoptic segmentation. And you can imagine very easily that this is increasingly challenged. It's harder and harder to get this level of detail and granularity out of your data. So that 70% of your time may start to balloon to 80 or 90% of your time as your task complexity increases. Now, synthetic data has possible advantages here. So, right, it is automatically labeled, so there's no human annotation required. And because of that automatic labeling, you can get increasing levels of granularity without any extra cost of annotation time. It's privacy compliant because it's fake, so no real people were used. It is highly iterative, which means you can update and generate new variants of your data, add new labels to your data programmatically. It's affordable because you don't have to hire huge teams of annotators and data acquisition companies. And in principle, it is representative, right? We're able to adjust the domain, shift the distributions programmatically and iteratively so that we're able to make systems that maybe are able to handle so-called out of distribution data or so-called distribution shift or domain shift problems in production. So in the workflow you might have for synthetic data, you would build an environment with something like Unity. You would then use that environment to automatically generate labeled images. You train your computer vision model as before, you evaluate your computer vision model as before, and you deploy it. And here, when you want to iterate on your model based on your evaluation or deployment steps, you can say, oh, I need to shift my data. Let me go back to the environment and apply the shifts. I need to update the labels. I realize I want to go to panoptic segmentation because that'll help my end business metrics improve. You can just update the labeling. And this can all be done programmatically and easily. So you're not spending as much time. Now, that's well and good, but that presents a new challenge, which is how do I build these environments such that I am able to handle the complexity and diversity of the real world? So this is a method that has been proposed for a while now called domain randomization to bridge the sim to real gap, which sim to real here meaning simulated data to real world performance gap. Okay, so domain randomization is a simple to state idea, but complicated maybe to understand, in which you we use a synthetic data generator built in Unity or otherwise to generate the most diverse data that your model can handle by varying various properties of your simulation. For example, the location and orientation of your objects, the color and texture of your backgrounds, lighting, the presence and diversity of optical occluders, the camera position, orientation, and field of view. And by creating the most diverse data that your model can handle, your model is able to effectively learn the most general separation or classification or regression solution it needs to learn. So we can break up these randomizations, these variations. We can do this in real world data as well as synthetic data into what we might call intrinsic and extrinsic variations. So think of intrinsic variations. These are somewhat task specific definitions. So allow me to define these in the context of something like object detection or panoptic segmentation or semantic segmentation. Instance segmentation. So they would be intrinsic aspects of the target objects. So the shape, texture, color. And we can think of those types of variations as being simple to complex. And extrinsic features might be things that are examples of the environment. So they are the camera positions, the object placements, the orientations. Often we consider, and we can think of these as structured and unstructured. And a lot of times when we're building a model that we'd like to be able to produce, to work generally, that is to be generalized to many situations, we want them to be sort of invariant to some of these variations. Which ones depends on the exact task and problem we're trying to solve. So, for example, if we wanted to say, hey, I want to detect a specific type of shoe, like some sort of a Nike shoe or something in my store, very specific model. So, Nike Jordan Air Max 1s or something. That's a very specific and unique object. And we want to detect it sort of anywhere in the world. So we really don't want us to be invariant to all the extrinsic variations. And we have a very singular or simple object, a simply defined object, uniquely defined object. So we might say this is a simple intrinsic variation and an unstructured environment. Maybe you want to detect shoes, the concept of shoe anywhere in the world. Well, now you have a very variable intrinsic, right? You can change its shape, color, texture, so forth. But also you want to detect it in a very general sort of sense. So you want it to be in a very, you don't want to be sensitive to extrinsic variations. So then you might say you have a complex intrinsic variations but still unstructured, complex intrinsic variations, very simple unstructured extrinsic variations. Now, maybe you want to detect a specific IKEA furniture in somebody's home. Well, now you're talking about something that is very specific, but also in a very specific environment. So now you want to consider the structure of your environment as well as the specific structure of your target object. So that would be simple and structured. And then you can maybe make something very, very generic, which is say, I want to detect people in a home. Well, that would be very complex variations. People would have many types of variations, but also in a specific set of environments. So in a very structured set of extrinsic variations. Okay, so this is like 4 types of examples that put us in our 4 quadrants of intrinsic and extrinsic variability. And these are the sorts of types of variations we need to embed in our environments that we're creating to create synthetic data for this problem. Okay, now that applies a whole set of now burdens, because suddenly we're saying our environments need to be able to swap, could in principle need to be able to swap lighting, camera, position of objects, textures of objects, textures of backgrounds, presence and lack of presence of occlusions. This is a much more complicated environment than we are, or it's a different, I shouldn't say more complicated actually. It has different properties than a standard game environment. So we might think of, therefore, there are 4 levels of this kind of content. Today, we'll be mostly focusing on this visual aspect, in which we're talking about the visual fidelity of our system. So the renders so the objects and content in our environment renders correctly under a wide range of conditions, and the appearance can be varied. The textures, materials can be changed programmatically. But as we go up the complexity of types of machine learning we like to do, we can think of more and more complex types of content. So we might need it to be physically realistic, because maybe we're building a robotic system that has to interact with some of these objects. So then the assets need to have accurate colliders, their mass and density would need to be varied, friction coefficients, etc. Furthermore, we might be interested in the kinematics of our objects. We might be doing object tracking or other types of problems like that, in which case the objects have to be rigged and animated. Objects in the same class should share rigs and animations. These animations should be varied. So maybe we're doing person tracking in the scene. Next, we have the final layer, a level of content we might be called fully embodied, which is not only that the content can move, it can be interacted with, it is visually correct, but also it reacts to other objects, other agents in the scene. So maybe you have a person walking through your scene, picking up a vase to move it. Now you've gotten a very complicated sort of environment, much more like a game, but we can imagine that from a content standpoint, this has to be very real. You have to have both the visual realism, physical realism, and kinematic realism, plus the embodied intelligence. Okay. So if we focus today on just the visual with a touch, a hint at the kinematic, we realize that there are some things we need to consider specifically. So meshes of our content should be free of all defects that would cause rendering artifacts, including but not limited to, having coplanar and laminar faces, no zero areas, well-behaved non-manifold geometry, so cannot be unfolded into flat areas. Faces are, that are self-intersecting have to be removed. Unattached vertices have to be corrected, smoothing and soft edges. You also need to have a careful thought about the UV layout set because we're going to swap textures and materials, so they have to be distortion-free, et cetera, et cetera. All of this is to say, our content has to basically handle the complete set of possible conditions it could be in, because we're going to end up randomizing and varying it depending on our problem. Either we're going to be swapping its textures, we could be swapping its locations, its orientation. So all of it has to be renderable and very well behaved. Standard game content does not have to adhere to all of these requirements, though I'm sure most game developers would like them to. So I shouldn't say that this is unique set of requirements to computer vision, but they are a necessary set of requirements for computer vision, whereas they may not necessarily be required for game development. Okay. So now we've talked about lots of the problem of why we need synthetic data, how we could create that synthetic data, and the burdens that applies to our systems. Now we should talk about, well, now what can we do to help? How can we make this easier and smoother? So in a very simplistic way of thinking about it, we've created sort of 3 sets of tools, all wrapped together into something we might call the perception package and sensor SDK, that allows us to instrument our environments with sensors, labelers, and what we call randomizers. So sensors, ways of capturing images that can be used as input for computer vision models. So RGB captures, RGBD captures, point cloud captures, LiDAR type captures, all these sorts of things. Labelers, ways of labeling the data in a way. So this is like our Y. So sensors gives us our X or inputs, Y's are labelers gives us our Y or our outputs. And so those can be, as we said earlier, bounding boxes, semantic segmentation, panoptic segmentation, instant segmentation, all kinds of 3D bounding boxes, et cetera. And randomizers are these ways of varying the intrinsic and extrinsic properties of our scene. So these are statistical definitions of our environment. So the sensor SDK has itself sort of 3 layers, which is, it's all built on top of something called System Graph. This is for Unity specifically. So System Graph, on top of that, we have the SDK, which has sensor components and camera components, as well as a library of sensors, so specific camera models and specific LiDAR models. The perception SDK comes with the ability to write custom labelers, but also comes with a large number of off-the-shelf, ready-to-go labelers, including bounding boxes, 3D bounding boxes, instant segmentation, semantic segmentation, not shown here is panoptic segmentation, which is the combination of instant and semantic segmentation. And these allow us to, if content is appropriately tagged in the environment, automatically generate the requisite labels. We also provide randomization frameworks for both structured and unstructured or semi-structured randomizations. So that includes placement and lighting and camera and all of these things, as well as relational or dependent randomization. So if you want to create something like a house, you can say, I'd like the windows on the right, a bay window on the left, etc. So you can make relational connection. So you can sort of see the different kinds of randomizations. So those are like the basic suite of tools at a very, very high level that we provide off the shelf to try to advance this area of research, the use of synthetic data for training real world models. Now I'd like to talk about a very specific example that we did for human-centric computer vision. So here, this is a environment we called People Sans People. This is open sourced and readily available. The only part that is not available, so I'll get into that towards the end, but some of the specific content, we provided the binary as well as the environment, but some of the specific content due to licensing reasons cannot be provided off the shelf, but it should be easy enough for people to import their own specific content by signing up for that license with Render People. So here we have 28 human assets in the environment from Render People. They come with a diverse set of animation sequences so that they can be posed in complicated ways, a wide range of clothing textures that can be applied. They're quite wild. We have parameterizations for the placement, the lighting, the camera system, existence of occluders and distractor objects. This system comes with an RGB image capture with using the high definition render pipeline community. Comes with a full set of labelers, including the key point labeler for human pose estimation, package binaries for both Mac and Linux. Apologies for the Windows users out there, we do not have a Windows binary. And CLI and configs so that you can update all the parameters and generate as much data as you'd like. So, okay, so I'll highlight a couple of the interesting and unique randomizers. I think things like placement and backgrounds are pretty clear, but maybe the animation randomizer is not. So the animation randomizer allows us to take these characters, they share a common rig, so we can use animations across them. And by cycling through the animations, taking random keyframes in the animation, as it were, we can create a wide range of poses for all of these characters. So here you can see them going through a wide range of weird and interesting and fun poses. This set of animations have been selected specifically to allow for the widest diversity of human poses we can. And by using these sort of off-the-shelf from Mixamo animation rigs, we sort of guarantee that there are no poses that are unreasonable or unrealistic or impossible. Another important one is the clothing texture randomizer. So here we're using ShaderGraph again, just like we do for the Sensor SDK. And this allows us to specifically take the clothing and randomize the UV layouts of them so that we get a wide variety of different clothing textures that are available. Like I said, we have maybe over 20,000 such clothing textures. So there's a lot of variability that you can do, including crazy things like having somebody have an iPhone for a t-shirt. As well as it also allows you to add some wrinkles because you also can alter the normals a little bit too, which is nice for our diversity of the system. And all of that being put together, you end up with some wild looking stuff here. So here you go. So these are on one side, you see just the raw images. You can see people in crazy poses. You have these objects and backgrounds that are kind of nutty. And on the other side, you see them fully labeled. Here you're seeing bounding box, instant segmentation, semantic segmentation, and key point labeling. But of course, we can add the instant segmentation. It's easy to add as well. Okay, so that gives us a data generator with a rich set of possible parameters. Now let's see how this works against using real data. So again, our intrinsic variations for our 3D objects, we have sorry, our randomizers can break into textures and colors, 3D objects. We have background includer placement, object placement, scale, et cetera, et cetera. Wide range of possible things that you can change. We also have a wide range of things you can change about the camera lighting and post-processing effects. And again, so now we're armed with a binary called people sans people, that's a wide range of exposed parameters that we can now test and benchmark the performance of. So first thing I'm going to show is distributions, statistical distributions compared to a well-known open source data set called COCO. So if in case people aren't aware, COCO was Common Objects in Context, presented by Microsoft, built many years ago, and has around 60,000 real-world images of people with key point labels and so forth. So here we're looking at just taking the off-the-shelf, so taking COCO as is, as well as using our, say we call default parameters, so the default ranges of all of our randomizers. And you can see that using our default parameters, we're able to capture the extent of number of people, number of bounding boxes in a single image. So that's the number of labeled people in a single image, as well as, we encapsulate the relative size of those objects. Here we're seeing, this is quite a nice, a heat map of the bounding box placements in the image. On one side, you have COCO. The reason you're seeing this sort of all centered in one corner in COCO is actually because not all the COCO images are of the same size. So you see this like aliasing effect. So you can kind of see those corners, but really you can say COCO is pretty uniformly distributed across the image, as is the synthetic data. So these are again the placements of people. So what we've done here is a heat map of bounding box locations in the image. Here we're looking at the heat map of poses, and I'm only showing 5 key points rather than all the key points because it gets a little too noisy. But we do have a white paper, and you can see an archive paper that you can see all the details of. So here, what we've done is we've rescaled all people to be the same size. We are then, so this is in a unit curve. So the unit 1 is actually the size from the hip to the shoulder. That length is uniform. You see the heat point of the nose location. We've also centered, of course, everybody to overlay them. So the centering point is the midpoint of the hip. So that's 0, 0. So here you can see the distribution of the nose key points, the right wrist, the left wrist, the right ankle, and the left ankle of all characters in COCO. In the COCO in red here, you can see that there is a symmetry, a broken symmetry here, in which people are mostly facing towards the camera. So some people are facing behind the camera. It's on average facing towards the camera. That's why you have more of the right wrist on the right side and more of the left wrist on the left side. Conversely, with our data, the synthetic data, using the default parameters, of course, these parameters can be changed to alter the distribution, but using the sort of default largest extent parameters we can generate reasonably, you see that we break that symmetry. So people are equally likely to be facing forward as backward. You also see a more diverse general set of poses, right? People are sometimes, as you saw in that animation, doing breakdancing type moves, so you can get more complex set of poses are available to you. Whereas in the real data, it's sort of fixed. This is the distribution, and you can't really, other than doing some clever data augmentation about flipping images or something, you can't really do much about this. And even if you flip the image, you really wouldn't be changing left, right. You'd still be front facing, right? So, okay. The other thing you get, as we talked about, is improved label consistency. So though COCO is a remarkable data set, it's sort of somewhat known to have some slight label funniness in that not everybody wanted to label all the things all the time. So there's a large number of images, for example, with people in which they didn't bother to label the key points because it was time consuming and the annotator didn't want to do it. And in many images, not all key points are labeled, either due to occlusion or otherwise. In our system, basically, as long as all the key points are visible, they can be labeled. So all 17, these are the 17 Cocoa key points. And you can look at on the other side is the specific distribution of each individual key point. You can see it's quite uniform. This means that our data comes by nature to be sort of unbiased in terms of, or balanced in terms of key points. So it's, or the model should be equally likely able to predict any given key point. Okay, so here we're just going to present a very basic baseline training method, which we're going to train on synthetic data, a standard model. So here we're just using Detectron 2. After training with synthetic data, we'll test on real world data, but we'll also fine tune our model on the target real world data, Cocoa. There's no weight freezing, nothing complicated here, just a low learning rate, fine tune the model, and then evaluate everything on a true held out Cocoa test set. So I'm sorry, I'm going very fast. In the interest of time, I do want everybody to make sure we make our coffee break here. So here we're looking at the models trained for both bounding box and key point detection. Trained from scratch means trained on, means no pre-training. We train from scratch on synthetic data. Means we train from scratch means we train on only real world data from scratch, the Cocoa data. ImageNet pre-training means that we are taking a neural network that has already been trained on ImageNet and then fine-tuning it on Cocoa. And synthetic pre-training means we take nearly 500,000 synthetic data frames from People Sans People, train our model, and then fine-tune on the real-world data size listed here. So for 641 real images, of course, if you train from scratch on 641 real images, you don't really expect to do very well. Using ImageNet pre-training, you do much better. But using synthetic pre-training, you do way better yet again. And this trend holds even as you get to very, very large amounts of data. So here, again, I'm presenting just the average precision of each of these metrics. So even up to, say, 64,000, which is the full Cocoa set, if you use 64,000 images, train Detectron 2 on those, you get about a 56.7 bounding box average precision. But with synthetic pre-training, we can push that even a little bit. This effect is a little more dramatic when it comes to key point detection. And again, most of this effect is happening when we have limited real world data. So, okay. Here are some examples. So here we're taking that line where we've trained a model on, here I'm just showing, so we pre-trained the model on ImageNet. We've then fine-tuned it on 6,411 Cocoa images. And we're comparing that performance to what happens when we use synthetic pre-trained data. We've trained the model on 500,000 synthetic images and then fine-tuned on 6,411 images. And here you can see that the types of false positives get removed. So using an ImageNet pre-trained model that has been fine-tuned on Cocoa, you end up getting these false positives where zebras are people and planes are people, and maybe for some reason this mouse is a weird spider person. With synthetic pre-training, we remove those false positives. Also, we refine the pose estimation. So here you can see a higher quality of pose prediction, though not perfect, I should say, but higher quality pose prediction for a number of people that here you can see that have slightly funny and odd poses predicted via Cocoa, particularly getting things like legs confused or arms in odd poses. Okay. And here's sort of a nice, the summary plot. So here again, each color represents a amount of real world data used to train the model. On the x-axis is the size of synthetic data used to pre-train this model, and then fine-tuned on the amount listed for each color. And here I'm just showing you the human key point average precision. So you see in general that models improve with more synthetic data and with more real data. Not surprising, models are better with more data. Though there is a saturating effect around 250,000 or 150 images, so around 250K images, you start to see the model start no longer able to perform much improved performance. That is probably down to the model we've chosen. We're using a ResNet 50 background for Detectron 2, so there's probably some model capacity limitations occurring here. For reference, we can show what happens when you use ImageNet pre-training. So we can see that again, synthetic data outperforms ImageNet pre-training no matter how much data we're using for fine tuning, though that effect becomes relatively less as we increase the amount of real data. The other thing we may notice is that our zero-shot performance is not great. So we find that using synthetic data and then just trying it on real data tends to not work very well with this data generator using the, shall we say, most general set of parameters, wildest set of parameters we can use. So what can we do to improve that zero-shot performance? And there are sort of two sets of things we can think about. And today, one, which is we can do things like style transfer in the model, which should help improve the performance. But we can also think in a data-centric way about, is there better or optimal data that will allow us to learn this zero-shot, improve this zero-shot performance? And so this is an idea called, this is a meta-learning approach that has been used by a few people in the community. So, normally we have our simulator and our task-specific model, and our model is training and getting more and more data, and we're training our model. Okay. Now, we can either automatically, adaptively, or actively update the parameters of our simulator based on our model training. And again, a number of wonderful papers on this. Including automatic, adaptive, active domain randomization, MetaSim, and learning to simulate, all of which take the approach of trying to learn how to update the simulator based on the model performance at a given instance in time. Generically, we can look at this like needing to have some meta learner that is taking the model evaluation and learning to update the simulator. So this is sort of a second order learning or meta learning kind of approach. To do this, we have to instrument both our model to allow for this evaluation, but that part's easy because almost all models come ready to go for an evaluation thing. The key is to update the simulator so that you can update the configuration, the parameters easily. Luckily, PeopleSense People is designed just for this sort of capacity right now with the CLI, and coming soon, we will have a full Python API that will allow this to be even more seamless. The other thing we can do is think about, hey, use something more structured, right? The set of variations that we put here are sort of all independent and wild, and they can become instead dependent and more structured. So we can think about, hey, what if we just do people in a home? An example I provided. And we just want to be good at that. So maybe we need a home environment data generator and a people data generator. So we have our people data generator can provide that. So we have such a process using split grammar systems with a full set of objects that can populate that home like furniture. This unfortunately is not open sourced, so this is a project we call Escher, but it is still not available for everybody to use. But you can contact us if you'd like to try it out, and allows you to do things like this, where you're able to take a scene like this, very specific aspects of the scene, and it comes with a full suite of labels that you see. Right. And hopefully this video is playing okay. I know sometimes the videos can be a little choppy over Zoom. Okay, just the time, move on. Another environment that will be coming out, just to keep advertising that we'll be putting out, is an environment specifically for our friends in the robotics community around 3D object pose estimation, in which we'll be using standard set of test objects that the robotics community uses called line mod, and allows you to sort of create these sort of wild and crazy variants of positions where you get the 3D bounding box of a specific object from line mod. This is very useful for robotics systems where they are trying to determine where something is in order to say, pick it up, manipulate it, move it somewhere else. So, and this environment will also come with all the physics and colliders available so that you can actually do that robotic manipulation on those objects as well. And that should be coming in the summer. So, in conclusion, and hopefully we are not too far over time and everybody can make their break, synthetic data, we believe, can be the future of model training, but it is hard to make and use. So we are providing a set of tools and environments to encourage researchers to start working on this sim-to-real problem. So one is People Sans People, which is a free to use synthetic data generator, which I talked about, and we benchmarked for everybody. So all anybody has to do is beat us rather than having to re-benchmark everything. We've done, we have a 3D object pose estimation environment, which will be available actually in the summer now. We should have it finished. We also have demonstrated that synthetic pre-training outperforms real data pre-training, but our zero-shot performance is not where it should be. And so we're also providing tools to allow us to try to find optimal parameters to either match or encapsulate distributions of any target real-world data. We will also be hopefully releasing a paper soon around ways to do actual sort of model style transfer type shifting to bridge the sim-to-real gap as well. But that's sort of model centric and not data centric, so not maybe the thing to talk about here. Anyway, so thank you for your time, and I think I just made time, so thank you.
Thank you, Sujoy. Appreciate the talk. So everybody, we're running just a few minutes behind, so we'll come back here at 3:40. So we'll just shift by the half hour a little bit. So we'll meet everybody here at 3:40. We'll hear Florent's talk on machine learning in real time. So we look forward to seeing you then. Thanks.
So, hi everyone. My name is Florent Guigné, and I'm going to speak of machine learning in real time as a follow-up to the tutorial. I'm going to go roughly for 40 minutes, and after that, I will have a conclusion by Carl and a QA session. Let's go. So, I work in a part of Unity, which is called Unity Labs. And what Unity Lab is about is to look forward in the future to see how games will be, games on real-time 3D actually in general, will be authored and played. So we have various areas of interest, such as authoring, AI and deep learning, which will be a focus today, computer visualization, XR, and storytelling. So I work on a team called Barracuda. And what is Barracuda? Barracuda is an inference engine. So what does it mean? It means that it takes a neural network and make it, it executes the neural network in the context of the Unity engine, in that case. It's cross-platform, and it works on both CPU and GPU. And there's going to be detail on all of that. An interesting thing is delivered not as part of the engine itself, but as a package. So you can check the link on the slide note after the fact. And you're going to see everything we do, all the source. So all the kernel, all we schedule the things, everything is there. And so the question is, why do we do that? So from the previous presentation, you guys have seen a ton of very cool examples of how machine learning and real-time 3D can go together and be super powerful. So I'm going to look a little bit more into that to provide some example of why it is so exciting, why it is so powerful. And then we will move to actually, then you get a model. It was trained with all the previous techniques that were presented, and you want to run it on device. So yeah, use cases a little bit, then the pipeline, how do we take an ONNX model and bring it to device, running on device. Once you have a model that's actually run, it's very important to run as fast as possible. That's an enabler. If you don't run fast enough, then a ton of use case won't actually be practical. So we'll take, most of the talk will be about that, about optimization. And at the end, it's going to be a practical example where we took a neural network from a research from one of the guys that work on the research is actually in the room, I think, Kenneth. And then we took that research and make it, optimize it, both at the model and at the inference library level to have something on device. And there's going to be, there's bonus slides that I won't cover about converting your model to ONNX. So if we look at use cases, there's two broad categories. The first one will be medium computational intensity, and that could be smaller input size in terms of the amount of data that you consume. It could be complex architecture, it could be recursive architecture, and it's usually very nice to map it to CPU. It could be, for example, a system where you need low latency, or you need your data to get fed back to a system on CPU. If, for example, it could be your physics if it runs on CPU. And then the second aspect will be high computational intensity, where a typical example would be if you provide an image, if you do style transfer, if you do image segmentation, where an image actually a ton of data, so you need a lot of value to actually go through that content. And that's model that usually work with convolution, and that are better suited for GPU, where you care more about the throughput than the latency. So, medium computational intensity. We'll see two examples, there's many more. The first one is decision-making agent behavior. So what if your traditional AI could be improved or made more flexible and use a reinforcement learning technique? So this is Just checking something, sorry. Yep. Doesn't work anymore, yes. For to do that, you could use the ML agent package. That's also a package from Unity. The idea is you train your reinforcement learning algorithm in Python, and after that, your model is executed inside of the engine using Barracuda. It's very powerful, and there's two aspects to it. If you are a researcher into the field, it brings you the power of the Unity engine. So you get the fast iteration, you get assets, you get everything that a real-time 3D engine can bring to you. And if you're on the other end, for example, a game dev or someone that actually touch into a reinforcement learning without being an expert, then you can take that library and actually get the best, the latest of reinforcement learning for you without knowing about it. Another example will be animation authoring. So Unity Labs produce paper. If you go into the slide note, you will see a link to see to the publication. One of those paper is called ProtoRace, and the idea is you take a model and you will make it. Be an animation. You will make the model understand what a human behavior is in terms of poses. And then you can just move a little bit the anchor, and the network will actually create a pose that will look natural. So why is it so powerful? It's because then if you are an animator, you work way faster. And if you're not an animator, you can produce work that will look realistic without the training that an animator have. So it's basically cutting down the authoring cost by a lot. Let's move to high computational intensity. So there's 4 examples that we will look at. First one is super famous. It's super resolution. So the rough idea is a device go with more pixel, more resolution all the time, and that's not going to stop. But the amount of computation that we have to handle those devices is not growing at the same speed. So we need a way to reduce the amount of computation and still produce the great quality that we want. Super resolution, you actually render a downscale version, and then you use some technique to upsample. And this should do upsampling and anti-aliasing. So there's traditional technique to do that, and there's also machine learning-based techniques such as DLSS. And the machine learning-based technique have proven to be superior, at least as of now. So that's one area where machine learning is very, very interesting. Denoising is also another example. So I don't know if you can see that, but there's a lot of noise in that picture. So in terms of path tracing, having the first ray, the first hit, it's going to be somehow fast. But if you want to go to conversion in a picture like that, with transparency and things like that, it's going to be super slow. So there's no way you get a perfect picture in real time right now. So you will need to rely on denoising. And that's an area where machine learning shine. Style transfer is also an example. So let's say you have a texture or an image, and you can split that image in two subjects. One will be the content of the image, and the other one will be the style. So if you can do that, then maybe you can replace the style by something else. And that's basically the premise of style transfer, where you keep the content, but you change the style. And machine learning is able to do that with limitation, but it's very promising. And the reason it's promising is because if you look on the right, there's 5 different styles applied to an image. If you want to actually try in your rendering pipeline with all your assets, the artistic pipeline, to try this 5 ideas, it's going to take a long time, a lot of production cost. But if we can manage to have style transfer to iterate super fast on there's different artistic direction, again, it's going to be very powerful, both for creativity, unleashing more ideas, and for the cost of producing that. The last example we will look is about size transfer. And then you get everything which is about XR. So XR is VR and AR, but here it's more about augmented reality. So every time you get a camera feed, then you can do a lot with machine learning because you can actually rely on the very old, if I can say so, field of computer visualization. So in that case, you have a human as from a video feed, which is segmented, where we get different features. You get segmentation, you get body part detection, and you get the actual skeleton. By the way, this is a demo by by Keijiro Takahashi, which work on Unity. You can find the link on the slide notes. Another demo from Keijiro as well, where this time it's tracking of object detection for human. And the last one, where this time it's about hand tracking. That could be very powerful to enable more interaction, different interaction with device around us. So there's a lot of very interesting and not solved yet challenge about all of this use case. And there's many more use cases. So I hope this presents a bit the power of ML versus real-time 3D. If you're not convinced, there's more. So we spoke more of real-time, but authoring is also is very interesting. What about texture upscaling and generation? Machine learning could be used to actually compress and decompress in a way that we haven't seen yet. We spoke of denoising for path tracing. That was more in the real-time context. But if you want to go offline, there's more you can do. You can denoise a screen space buffer, but you can denoise other kind of structure. It could be volumetric lighting. It could be anything. Smart authoring, so an example here will be you train a neural network and you make it understand how a human being will set up furniture in a room. And then you ask that neural network to help you place things. So again, to faster iteration, unleashing basically time so you can have more creativity. A neural network would be very, very interesting. And a bonus. At Unity Labs, we are also looking at building terrain from machine learning. So that's an example. So I hope now you're convinced that it's super powerful and the future is going to be very, very, very good for the interaction of those two fields. So now we have a machine learning model, a deep learning one. And we want to run it in engine. So we'll look at how do we do that in Barracuda. So that's very targeted to Barracuda, but the idea could be used. It could be a different library and a different context. I think the idea still stands. So on the left, you have a Keras PyTorch or TensorFlow model. And we will convert that, or we ask user to convert that to Onyx. And then the Onyx file will be plugged into the editor, process, and finally set at runtime. Something will happen at runtime, and let's dive. So you get your Python code or model. You export to Onyx. So to do that, all of those libraries actually have either natively or extension a way to export to Onyx. Sometimes it's a one-liner, it's very easy. Sometimes it could be a bit harder because the mapping between the library and Onyx might not be one-to-one. But in general, it's quite easy. Then you get your Onyx model, and you actually just put it into the editor. And Barracuda will do his magic. So what we do is we parse the Onyx file, and we create basically a different version of that model, which our own internal representation. Why do we do that? Why don't we keep the Onyx model? It's because it's performance reason, essentially. So Onyx has some granularity, and we need to be at least as granular, but we can be more granular if we have good reason for performance reason. So we do that. So this is the first part where you drop your model, we look at it, we analyze it, we optimize it, and we store it on disk. Then you create a worker. It's just a work we choose to say to create something that's able to take that representation and run it on device. We get a bunch of different workers. So from the top, Unity Burst HPC. So this is basically a CPU worker. So what is Burst? Burst is a Unity technology which takes a subset of C#, and so you don't have a full language. You can write only a part of that language to be supported by Burst, and it compiled that on targeting native code on target device. So it supports SSC, AVX, Neon, all of this CMD thing. Also, Burst is from the ground up design, so your code will be easily readable. So basically, you write C#, not all of C#, but very flexible C#, and you get on-device native code threaded. So it's really beautiful technology. So we use that, and that's the basis for our CPU backend. Then we get two different backends on GPU. First one, it's a Unity Compute. Basically, we write HLSL, and then we use the power of Unity in terms of platform, where this HLSL is cross-compiled to every single platform that Unity supports in terms of compute. Some platforms don't support compute shader. Then we have a pixel shader backend. So an example will be WebGL. And then we don't deliver that, but we have experimented. So the design of Barracuda allows to add more backend. You just build on top. And we did that for DirectML, for an API, for CoreML. So we try all of this API that allow to harness the power of a dedicated hardware on device. We don't ship them at the moment. An example for DirectML of why we don't, it's because DirectML requires DX12, and we have seen, all statistics show that a lot of real-time 3D customers we have actually use DX11. So we haven't put a focus on that yet. So now we have seen roughly the pipeline, and just that optimization part, which is very important. That optimization can be split into three aspects. So we spoke a little bit about simplifying the graph. That would be the first step we will look at. Then after that, so this is perfectly backend agnostic. No matter what hardware you're targeting, it's just about the graph itself, and we simplify it. Then you get the second path, which we call the subgraph kernel layout selection. So this time you look again at the graph, but you optimize knowing your target hardware. And then there's the last part. You get for your target hardware the best graph possible. You still need to have every single operator to be as fast as possible. That's going to be the last part. So let's look at that. So this is an example of a network. It doesn't do anything. It doesn't exist. It's just for demonstration purpose. So let's say we have a network like that. We get an input, 2 matmul, then matmul on the right, which come from constant, convolution, transpose, ReLU, reduce, transpose, output again. What can we do? So we get 4 different kind of optimization. Let's look. First, the matmul on the right, it doesn't depend on anything which is viable. It's basically get 2 constant, do a matmul. So we don't need to run that at runtime. So we basically compute the matmul at import time, store it again in constant, done. Then you get 2 matmul, and both of them get an input. One of the input is viable, and the other come from the constant. So because it's 2 matmul, 2 matrix multiplication, you can combine them. So we do that. We change the weight, but you have only 1 matmul. And there's an interesting thing. Let's say the 2 transpose here are inverse to each other. So basically, the first transpose do something, and the next transpose do exactly the contrary. And in the middle, you get a ReLU. A ReLU could be anything, but basically the idea is that it's an element-wise operation where you don't care about all the memory is. So a transpose ReLU can be before or after the transpose. Transpose have no impact. So we could move a transpose. After the ReLU will be the same. But radius is a little bit different because radius will need an axis, and the axis might change because of a transpose. But we can compute that. So we look at operator between the transpose, and if we can, we change. And because both transpose were the same, we can actually kill them. So we just gain twice the bandwidth. And then we get a convolution, and that convolution are very ALU intensive. It's like the main problem in convolution. ReLU, on the other hand, don't use a lot of ALU, so it's all about the bandwidth. You load the data, do very little something, and then it needs to store the data again. So basically, we could take the ReLU and put it in the convolution. We do that. Okay, so here we are. You get this network compared to the network before. It seems faster, but actually, is it? It depends. If your network was bound by some of the things we removed, then it's going to be faster. But if the thing we remove were not using a lot of latency, not adding a lot of time to the inference, then it's not going to change anything. And so here's a graph that shows that. Basically, what we did is to run inference before and after optimization and look at it. So on some popular network. So on efficient net, we gain 1%. It might be that there's one gigantic convolution that's taking 99% of the inference time. Then you can remove the network to that convolution, and it will still be 1% gain. MobileNet, on the other hand, 26% is quite significant here. Okay, so we covered the graph simplification without knowing anything about the hardware. Just the graph is simpler. Now we want to look at the hardware we're targeting. And because we know the hardware, we can be a bit more smarter and still continue to alter the graph. So because you know the hardware, you will know what operator need. And some operator, for example, convolution, will need a particular memory layout to be efficient on that particular hardware. So you will need to, but one thing you could do is to put a transpose, do your convolution in an optimized way, and then transpose again. But that will be, you will probably have too much transpose in your network, and you could do better. So you can try to move those transpose away. And that's basically what that part is doing. You look at operator, you look what is the best way to run those operator, and then try to optimize the network again to remove as much as possible all of those transposes. So up to Barracuda 3.0, which is cheap, the way we did that was to have a flag at the worker level where you can choose your memory layout, which was useful, for example, for dedicated GPU. On the upcoming work-in-progress Barracuda, we are pushing the idea where it's going to be per subgraph and fully automatic. So we have covered the first part where we actually look at the graph, we don't know about the hardware, we simplify it. Then second part, we look again at the graph, but this time we look at the given kernel we want to run, and we optimize again. The last part, now we have a perfect graph, let's say, is to have the best operator possible. So matmul, convolution, etc. So let's take a look at two very famous networks, ShuffleNet and MobileNet, and just to get an idea, what do we need to actually optimize? So MobileNet, it's a 68 layers model, and on that there's 54 convolution. So it's basically only convolution. So when you want to optimize MobileNet v2, you want to optimize your convolution because the rest of the time is actually very little. It's probably 10, I can't read, but a few percent is not convolution. So convolution, super important. But then, other story, ShuffleNet. ShuffleNet, this time it's 182 layers, and around a third of those layers are convolution, dense, matmul, therefore is convolution, but those kind of operation. Which means you still need to optimize those convolution, like very, very, very well. But you still have a third of your network, which is, in that case, it's transpose and global average. Yeah, it's mostly transpose, a lot of transposes. So basically, what it means is that there's a few operators that you need to put a ton of optimization effort, and that's a very, I would say, lucky aspect of machine learning optimization, where a few operators are so important that you can really push optimization very far. But it doesn't mean you should not optimize other things. Other things need to be very fast as well, just maybe 1-2 pass optimization, not 10. So optimization, let's take a look at some things we do to make things fast. So on CPU, we get parallel block matrix multiply. So basically, we optimize our matmul, and we parallelize on the leading dimension. That being said, let's speak about convolution on CPU. So the usual scheme in terms of convolution is to go into call. So basically, you take your image representation in terms of memory layout, you transform that to a matrix, and then you do a matmul. The reason why we spoke of matmul just before. The problem of that is, as you can see here, you go from a 3x3 input with 2 channels, so 18 value, and you actually get 32 of them. So you just use more memory. And that's an example where it's not that bad, but if you take a more common example, like 256 by 256 texture, 3 channel, it's actually 10x more memory. So we can do that. At least not in the context of Barracuda and on the edge inference in Unity. So we do something else. Oh, this explains the integral algorithm. So you get the kernel size. So this is the kernel. And you unfold them here. And then the yellow one here. So we go and then we move the kernel. We slowly build the matrix that will be sent to the matmul. Here it is. But we can see that values are replicated. So this is a problem for us. Thus, we had to do something else with a better memory characteristic. And in general, because you want to target edge device, you need very good memory characteristic. So what we do instead is to have not one matmul, but k by k matmul, which, because of our implementation, allow also to go wide. So it's good for, it's a good fit with the way our matmul is working. So how does it work? Instead of doing the matmul like we did before, this time we just consider a little. So basically the 2x2, in this case, is a 2x2 kernel. So we consider a 2x2 kernel, and we only do this with the associated weights. And we move, and we continue. So instead of one gigantic, not gigantic, but one matmul, we do many. So there's a little bit of, I'll go back here, we'll see that later. There's a little bit of extra ALU needed for that, but it's actually not that much, and memory is much, much better. So that's a consideration we have to take. So here we can see that actual matmul job, so matrix multiply job. So it's compiled in that case to x64, SSD4, and you can see the CMD intrinsic here. So that's a demonstration or burst compiled to native code. And again, this is a matmul and into call slice. So we can see here job dependency. Probably not very clear like that, but this is the Unity profiler in terms of job, and you can see the dependency, where one matmul will spread and do a ton of thread, all with dependency. In general, burst, the way it works for our Barracuda implementation is that you will schedule everything, and all the job will just depend on each other. and it's basically asynchronous. And at some point, even if you're on CPU, you want to get back the result, you wait for it. But the job are a chain of job. Okay, so that was a peek into our CPU implementation. What about GPU? So GPU are obviously very different from CPU, but they are also very different between each other. So the most obvious difference will be the GPU you have, or the kind of GPU you have on mobile, and the one you have when you are dedicated. For example, on-chip memory. So on dedicated GPU, you have on-chip memory. But on mobile, you don't. It depends. Some mobile you have, but you can't really rely on it. It's not as fast, it's very different. So that's some very, very important change. You can't have the same algorithm. It's not gonna work. If you use an algorithm that was designed for dedicated GPU using on-chip memory, and you just run that on mobile without looking, you may end up actually trashing your cache and being slower. So it's very important. Scalar register exist on a dedicated GPU, and they allow to lower the register pressure, but on mobile they might not exist. So again, we did an optimization, will not apply. You need to find another way. When we speak of dedicated GPU, especially for convolution, the bandwidth you get from that on-chip memory versus the IU you get, the ratio is different between AMD and NVIDIA, for example. So that's also something you need to look at when you do your different algorithm. And there's more. Number of threads to saturate your GPU. Not every GPU gets the same amount of hardware thread. So there's a ton of consideration. Basically, it's boiled down to you need to look at use cases, categorize them, then hardware, categorize them, and have a ton of different implementation. And you can take a look at all the implementation we have in the source code. So a bit more about GPU. In general, you have a warp size of 64 or 32, sorry. It mapped nicely to, we'll speak about that later. It mapped nicely to kernel if your data is actually have a 64 channel, for example, then it's quite a natural fit. But what if your data is actually with a lower input size, 32, even 16 in terms of kernel? Then you will need to have other algorithm, and it's probably going to be harder to actually have a good fit with the hardware. So that's something to consider. It's especially true with, let's say you get a neural network which take a convolution at the beginning and at the end because it needs to go back to an image. So it's 3 or 4 channel. It's going to be quite hard to get perfect or near perfect GPU utilization on those convolution. So that's something to take care when you do the implementation of the convolution, but also ideally when you design the model. If you start your model with, let's say, 9x9 convolution on a 3 channel, it's going to be probably very bad GPU utilization. Yeah, and there's various ways to implement a convolution. Winograd is a very interesting one, but it's limited. The technique have benefit and limitation in terms of the shared memory it uses. So it's not applicable for every single input. Okay, so we spoke a little bit about memory layout. So what does it exactly mean? So here we get 3 different memory layouts. So on the left, maybe we'll start on the right. What you get on the right is actually what is contiguous, linear in memory. So in that case, for that transfer, W, so if you get something which gets the same N, the same C, and the same H, but just one difference from W, for example, 2 and 3, it's going to be contiguous in memory. So you get, this is contiguous, this is start to be less, less, and less. So basically, it's mapped to caches and the way accessing memory work, where if you access memory, you want to use your caches in the best possible way, which means you want to access data which is close to each other in terms of memory. So some algorithm will require to access, so some algorithm don't care, but some algorithm will require to access maybe, actually not, I don't know any, but let's say there's a W linearly, and then you will have this kind of memory layout. Oh, yeah, no, actually, for GPU, this is really good because, yeah, we need to dive into the implementation, but having channel here is very good for convolution on GPU, on dedicated GPU. This one will be interesting maybe for mobile, for example, on GPU. And this, not with 2, but probably with 8, could be interesting more for CPU. And the graphics show you all things map. Sensor memory layout. Yeah, so that's what we say. Where, let's say you're working on your convolution, you optimize your graph, and you want to be NCHW, to be faster on a dedicated GPU, then you will shuffle around. And we will do that by adding metadata to the graph. So now we'll look at a case where we took a research from a research lab grown up. So this is an amazing paper in the sense that what you see on the right, the model, so style transfer, there's various ways to do it. And the way they did it here is that you get a model that is allowed to take, it takes two inputs. It takes an image and it takes a style, which means the goal is that you can send a different style at runtime and iterate very easily on various styles. So we took that demo and the goal was to go from the performance, it's probably hard to read, but it was 40 milliseconds on RTX 2080 at 720p. And the goal was to optimize that to run at 1080p on console in real time. So we targeted 30 milliseconds, 33 exactly. So we started by looking at the model. There's a few things that came up. So the model, the way it worked was you first go downsampling. And the 48 here and the 32 here is the number of channels in your tensors. And then there was the residual part, which was actually applying the style, and then going upsample again. So the first thing we noticed is that 48, that was actually a bad fit for our implementation. Our implementation were fast at 64 channel. So yeah, basically 16. There's a quarter of the speed that was just lost because of that. And also the way the downsampling was in the model and our implementation was very slow. So that was two different things that we could look at. Changing the number of channels here and improving downsampling and upsampling. In terms of timing, convolution, we're taking a bit more than half of the time. And then we get, this is instance normalization. So this was a target for optimization as well. And a bit of very weird things. So activation, which should be very free, were still showing up in the profiler, broadcast as well, probably too many of them. So we dive a little bit into that, and we discover a few things. We were not having enough fusing, so we implemented that. Instance normalization needed to be optimized. We did that, and convolution as well. So we had a plan, and let's see how it actually worked. We had a plan, but we thought that even without all the target optimization, we had idea of the new performance that we will get. But still, it was very tricky. We probably will be very, very close to not reaching the performance we want. So we look also at downsampling the input. So basically doing the same, but having more downsampling and more upsampling. But it didn't work. Basically, the network was very producing a very dreamy look when we done sample more. So we could not do that. We did not reach the quality we wanted. Two little bugs that we encountered that I think could be interesting for the audience. The first one is, I think it's a consequence of Python and the ease of use of Python. So in Unity or in any rendering engine, your color format is very important. You need to control the way your color are expressed from the start to the end to actually have a proper result you look for. But when you load texture in Python, it goes to various libraries, and if you don't care, and we did not at the beginning, you will probably have mismatch where some will maybe loaded in sRGB, or maybe some will be loaded in linear, and it actually depends on both the library you're using and the file format you're using. So if you don't look at that, you may have later in your production or pipeline some very weird artifacts that you don't know where they come from. And it's actually, they come from the fact that the network is seeing input that it was not trained on because of the different color format. And then you need to go back to the whole chain to actually understand. And because of the black box aspect of a neural network, it's harder. So it's probably a good idea to assert the full pipe early on. Also, we add a bunch of ideas for optimizing the network, but because training is long and in some way expensive, you can't do as many experiments as you want. You need to choose your battle, which means we had to work on some, I would say, broken network, but we knew why for some time. Why still iterating on the code? Basically, you iterate on the rendering code faster than you can iterate on the NN training. So you need to, as much as possible, separate the, I need to go faster, separate the network iteration to the rendering. For example, we added, after the network, some LUT color conversion. So to try to get the proper artistic direction you wanted. And after that, on the final network, we actually removed those LUT. Okay, so the final architecture was actually not 64 as we expected at the beginning. We discovered that to get quality, we needed to keep the same depth of the network, but the width was not as important. So to gain performance, we reduce the width, but keep the depth. That's kind of sad story because we actually optimize quite a lot for 64 channel. But that's still, so there's still a lot of optimization that could be applied to that. And the funny thing is that, the final percent are actually quite the same. Just everything's faster, but apart from things like activation that you can't see anymore, it's a bit the same story. And the reason is because there's actually a lot of instance normalization in the network. So in terms of performance, we went from 40 milliseconds at 720p to, it's not the same model, to 30 milliseconds at 1080p, and a very different scene as well. So it was 12 milliseconds of inference. But for PS4 Pro, that was on PC on RTX 2080. For PS4 Pro, that was not an option. Still not enough performance. So Thomas Deliotte from Unity Labs work on temporal reprojection. So the idea is that you get just a piece of the input, you stylize on that, and then you use the depth buffer to reproject. So every frame, you basically do a quarter of the screen, and then you reproject. Maybe it's a video. Could you click on the video if it's one? No, okay. Then you can run this one. Thanks. Yeah, and this is the final result on PC. If you want to see the video for PS4, in the slide notes you will find a link to a blog post we did where you can see all the video. And can you run this one, maybe? Can you run this video? No, it doesn't work? Okay, then also on the blog post. Then that's it. Thanks a lot. This is just to say thanks to the full Barracuda team and also the global style transfer team. Kenneth, Thomas, Adil, so Alex, Rimas, Tracy, Mantas, Renaldas, for the Barracuda team. Thanks.
Hey everyone, thanks Florent for that great talk. Just want to do a brief recap of kind of what we've learned today here at this tutorial, and then follow that from we'll do a Q&A session after that. So we started out today kind of thinking about, the goals of this course was one is kind of understanding how to close some of these gaps from research to deployment. So we kind of looked at those in many different phases, whether it's from practical examples to data acquisition to actually kind of looking at a whole framework from Barracuda, right? Then we looked at some of the challenges we have for basically developing these models, training the models, many different areas that we can, and actually some solutions of how to tackle those challenges. And then the third aspect in the goals was looking at what are practical examples out there today. I mean, it's a pretty exciting time in this field if we're thinking about neural rendering and how that's changing. We're seeing it all the way from a lot of post-processing stuff, but we're starting to see how it's going to become more of an integral part of the pipeline. And it's also from content creation, how we're going to see new forms of how we create content using neural rendering. So it's definitely an exciting time, and there's lots of exciting research that you're going to see here at Eurographics and SIGGRAPH and beyond. Just to give a brief recap of the different segments, so we heard Deepak talk about, showing, there's some practical examples of how we got machine learning for content creation, whether it's codec avatars or many other forms. We even looked at kind of the machine learning for rendering and different examples there, whether it's DLSS or whether it's style transfer. And then one case is like, here's kind of the typical workflow, right, of how we would take a model, train it, get the data, reiterate, optimize. So this is kind of the simplified path in which you would go through when you're taking these models from the research papers down to deployment. And then we followed that up with Sujoy's talk on synthetic data generation. So he described many of these methods where you're starting to bridge this gap between sim to real data sets. Like you said, there's a lot of reasons people are using real data sets, but a lot of times there's a lot of issues of how you get the right data sets and do you have the licensing and other issues. He talked about some of the burdens of domain randomization, whether you need to do lots of alterations from models, locations and orientations, colors, textures, all sorts of stuff. It was kind of interesting seeing some of the work he was doing with the people sans people work, where you're seeing like an iPhone picture on a person. And then he has some later data sets that's coming out. Some of the 3D object work will be coming out, I think he said this summer. But definitely go out and look at some of the people sans people and others and try those out. And then as we just heard from Florent, this is a very powerful framework. I've used it myself. It's an easy way to get some of your models down into a rendering application. Use your buffers that you want, input it into the Barracuda framework. It's a package. You can easily download it and bring it into your system and start trying things out. So definitely I encourage you to do that. So kind of the call to action here is, download these frameworks, try them out. Unity's one of them. There's others out there as well. In the course notes, we have a list of kind of ML frameworks, rendering engines, tools to use, deployment frameworks, data sets, and then a whole bunch of different lab links from all the different labs, whether it's Intel or Meta or Unity as well. So a lot of things to go try out. Start looking at these papers, start trying to deploy them, start understanding what are the issues and what do you need to do in that space. But definitely, if you have any questions about this course, about anything that you've heard about today and you want some further insight, here's our email addresses. Feel free to talk to us through this QA, or after that, you can feel free to email us. I think several of us are hiring as well, so if you are interested, definitely seek us for those opportunities. And with that, I want to thank you all for attending today. We'll have a Q&A session now. I'll invite the speakers up for the Q&A session. And I want to thank my collaborators. It's been great to working with Florent, Sujoy, and Deepak, and yeah, it's been a really amazing time. But yeah, we'll go to Q&A from that. Any questions? We have people in the audience with.
Thank you for the talk. I have a question, maybe go to Deepak. He talked about the rendering, neural rendering applications. One is the final frame rendering. I think this neural network is used for only the last stage or part of the rendering pipeline. So when do you think the end-to-end learning could be, the performance or can be comparable to the traditional rendering? Is that in the near future, or what's your thought on that, end-to-end?
So the question is, can I have an entire rendering pipeline using neural rendering?
Yes.
I think I see that we'll eventually get to that state in various forms. I mean, I see in the early stages, we're seeing a lot of stuff on the post-processing side, but I thought we're seeing a lot of things like neurotextures. You're seeing NERF-based models where you can code and decode and represent. I think through the pipeline, we'll start seeing, I mean, right now we have hybrid engines of ray tracing and rasterization. I think inferencing will be another core part of that. So I think we'll have that in the near term. The full pipeline probably will take a while to get all the way through and have that as a real-time approach. But it's definitely something I see in the future, that we're going to have these algorithms for many cases where the neural pathway. I'll let Deepak or Sujoy.
I mean, I think it's going to get there eventually. I mean, we shouldn't kind of forget that GPUs have been fully optimized. The whole rendering pipeline has been fully optimized for like 40 years. So trying to kind of change just one aspect of it is probably not enough. We need to kind of think about the whole system, right? I mean, okay, let's say we have a neural representation. Right now, how do you change a pixel in a neural representation? How do you change a color? How do you integrate them together? And how do you accelerate them going forward? I think just because a lot of it keeps changing so often, I mean, do you have a specific accelerator for CNN? Do you have a specific accelerator for MLPs? I think there's still a lot of innovation to happen. How would you represent a neural scene graph dynamically? So eventually, maybe it's going to get there, but immediately there's still going to be this hybrid rasterization, ray tracing, neural rendering, maybe in the post-processing stages. I mean, it's like, yes, it's not running in real time today, but wait 9 months, it's running 30 frames a second kind of thing, right? So I wouldn't say maybe not in the next year or two, but maybe sometime soon after that.
It's not direct answer to the question, but I think one very important aspect about that, it's the current pipeline, rendering pipeline, is very flexible, and you can change a lot of things, and you need to change a lot of things to actually go through your production, which means, I think if we want to have an end-to-end neural network strategy for rendering, it will need to be split in a way where we can actually understand it, debug it, alter it, and to get production friendly, to be fast enough, to apply artistic direction or change things.
Hey, thanks for the talk. I have a rather practical question for Florent. So I hope I'm not going out of scope here. You mentioned that Onyx could simplify your computation graph if you have a neural network. So say I have a neural network that will be used in a rendering program, like Mitsuba, for example. Can Onyx also speed that up, or is it something specific for the use in your Barracuda program?
So let me know if I don't answer to the question exactly. Onyx, so by default, Onyx is, I would say, some kind of file format, but more a description of a neural network. When we put that into Barracuda, we take that description and we try to optimize it. But we're not the only one to do that. Actually, there's a tool in the Onyx ecosystem that can do that. And I think it was said before, if you use OpenVINO or TensorRT, they also optimize the graph. I think it's a quite reasonable things to do before executing it. Does it answer the question?
Yeah, it does. Thank you.
I guess in the same regards, I mean, Onyx, so when you're exporting to Onyx, I mean, like you said, it's a file format, it's just a standardization. Some features are, as Deepak was mentioning, in certain versions, your features may all be supported in the model, some versions they may not, so you have to be careful which version you're exporting to. But then you would take that Onyx model, load it into an optimization framework such as Barracuda or TensorRT or OpenVINO, those type of aspects. There's no more questions, and I'd like to thank everybody for attending, and hope you have a great rest of the Eurographics. Thanks so much.
So, hello everyone. Sorry for the delay. I think everyone needed this break, but then it started to be a bit too long. So we hope the fast forward is going to be okay. We have some logistic issues. So first of all, thank you for coming. We were very stressed by the conference organization. You've been sending us emails. We've tried to be reactive. And so we were feeling like maybe we were not controlling everything. But I had a lot of feedback today that were very positive. So I'm cheered up a little bit, and we can go ahead for the full week. So we welcome you today in Reims, which is a city in France. Everyone figured out this thing. And we host you at the conference center. This is not where we work every day, obviously. But this is a very nice congress center, and we're very happy to welcome you here. some center downstairs that she was managing all the batch distribution. And then we were not alone on this, so we are the researchers of the lab, but we also had some extra people from the university that helped us a lot. Some are here today. There was Arnaud Renard this morning as well, and Charlotte, who is helping this week. And also some more people from the general university organization. Some are the technicians of the university, some are in the accounting department of the university, some are the administrative department, and some staff from the that are dedicated to conferencing in our university. So they all help us, and we know that we've been running under delay for some things, but I can assure you that everyone is dedicated to the conference. And also we really had a very strong support for the people from the Congress Center that helped us setting up this conference. We've been in touch with them since 2018, and they've been updating us with the new facilities and the new things that were happening in the Congress Center. And so I would like you to applaud them and thank you for their help. So also you've met them around. We have 22 volunteers that help us with the conference. Some are from Reims, but many of them are not from Reims at all. Some are from somewhere else in France. Some are somewhere from Europe and other countries. I asked them to send me pictures, but I haven't received them yet, all of them. So maybe they can stand up so that you can recognize them in the audience. So all the volunteers, if you can stand up, please. So yeah, they've been already really helpful until now. So now let me present you the program chairs of the conference 2022. There are Min Kim from KAIS Korea and Raphaël Chen from l'IRIS in Lyon in France. So they will be giving a talk afterwards, so I will let them introducing themselves. So, but they've done a lot of work as well. And then we have tutorial chairs, Stéphanie Amann, who is here, and Gustavo Pato from Girona University. So Stéphanie is from Grenoble. The state-of-the-art chairs, Daniel Menvo from the University of Poitiers, and Giuseppe Patane from the IMATI in Genova. And I haven't met him, but I know he's somewhere around as well. The short paper chairs, they were David van der Heg, from Toulouse, and Nuria Pelechano is around, so you can speak to her if you want. She's from Barcelona. The poster chairs, they are Basile Sauvage from Strasbourg, and he's here as well. He's sitting there, I've seen him earlier. And Yasminka Azik, who couldn't come today, but they've been working together. The educational chairs, Jean-Jacques Bourdin, who should be here somewhere, but okay, he's arrived now. And Eric Paquette, who's come from Montreal for this conference, from quite far. And the industrial chairs, there's Rémi Cozo and Oliver Groh from Intel, who has been working on the industrial program. The doctoral consortium are chairs by Julie Dean and Noska Smith, who are here as well. And the diversity chair are Noura Faraj and Diana Aureliano. So it's a new thing for Eurographics to have chairs of diversity, but we've been having diversity panels for some years now. So it became interesting to have also people that would do the work for that. And they are around as well, both of them. Yeah, just to come back, yeah, the diversity session is also supported by Disney Research. We have 4 invited speakers. So on Tuesday, you will see the talk of Sylvain Paris, who is on his way. He's coming directly from Boston, so he's almost here. On Wednesday, there's Jan Kautz from NVIDIA, who will give his talk online, but in this amphitheater. On Thursday, there's Ayelet Tal from Techno University, who is also going to be here. And Friday is going to be Mathieu Desbrun, who was at Caltech and is now settling down at the INRIA in France. We are very grateful to all our partners that supported the conference. We really couldn't have done it without their help because we had many expenses, and it's really great that they all help us. So we have local help from the university, the Reims city, the region, a partner as well from the CEA, and of course we have the full support of the Eurographics Association. And then we had other sponsors, industrial sponsors that help us, and some of them have a booth here, so you can go and meet them. So this is the map. I guess everyone arrived here, so you know where we are in the map, but I wanted to show it a little bit more. So you can see that the conference center is very near the train station, is in the border of Canal, and most of the hotels are the red dots that you can see here, and they are all in the city center. Many of them are in the city centers. Everything, if you choose a hotel that is not so far from the conference center, can be done, is at walking distance. You can go and run if you want along the canal. There's a path, a pedestrian path, so I hope some of you will take the chance to go there. And then there's the park as well. If you want to have a break during the conference time, you can go for a walk in the park that goes up to an arch, which we call the Porte de Mars, and which is quite nice and well known in Reims as well. So here is the main theater of the conference. Some of you that were here today for the tutorial, you already experienced it, and there's going to be some paper session here. All the common session will be in this theater, so we will have also the invited speakers here. And then there are 4 other conference rooms. So they are on the same floor on the side of the conference center, and there we will have other sessions, so paper session, tutorials, short papers, panels, and etc. Star papers that will take place there. And the people that were here today, we had lunch at the Millésime. So the Millésime is downstairs from this amphitheater. So we've tried to have very short lunches so that we could make the most of the day with the sessions. The meal is set with a starter, a main dish, and a dessert, and everything is served into a bowl. And so you can just take your bowl and then go to the table and enjoy your lunch. And someone will bring the main dish at the table for you that is going to be warm. So it's an experience. We had it for the first time at lunchtime, and many people enjoyed it. So everyone that are here and haven't had lunch here, I hope you will enjoy it tomorrow as well. We've tried to take into account all the diet restrictions that people sent us. If you have any issue, if you feel that something is wrong, you please come and talk to me or other organizers, and we will try to arrange so that everyone can eat as they feel that they should eat. So specifically, help us if you have any type of allergy or intolerance, and help us to help you with that. So the program was online for quite a while. We tried to fill the sessions one after the other as soon as we had the order of the sessions. So they are ordered to be a first column in the amphitheater, and then you have from room 1 to room 4. And you also have the detailed program in the red part down below on this slide, which are also below on the website, and you can follow the order of the papers in the sessions. So we have a typical Eurographics program. We have the paper sessions. We have the short paper session. We have the state-of-the-art session. And then we also have the education sessions that will start on Wednesday. There will be education session on Wednesday morning and a last one on Friday. There will be also industrial panel on Tuesday and Thursday. There's going to be a diversity panel on Wednesday afternoon. And there's the Wicked workshop that is going to take place on Thursday. You will also see that we've tried to book 1 hour for posters. So the presenters of posters, please be next to your poster in the afternoon for the 1 hour dedicated to poster. They are the same place as the coffee breaks, so that everyone can have a break, but go and do science and speak to the authors of the posters. We also have an area for industrial demonstrations. So some people have planned to show a demonstration to you. There will be an opening, a specific time that is dedicated to this tomorrow evening at 5. So there's 1 hour dedicated to this, so you can go there, and there's no other session in parallel. Otherwise, you can attend this booth if someone is there during the breaks, the coffee breaks, for instance. There are some mention of Reims city tour in the program. We haven't planned anything in particular. It was just time that we thought you should dedicate it to go and visit the city. There's going to be a link that we will send you maybe for some experience, champagne experience, but that's more or less what we've planned. So please go and use this time to stroll around the city. The main events are tonight at 7:30. We will meet at the City Hall, and Wednesday evening we will have the special event. The other events that are on Tuesday and Thursday are for restricted committee. So you've noticed that we are under a hybrid mode. That means that everything is streamed. Everything is set to be looked also for remote participants. It was complicated for us to set up this hybrid mode, and we've been asking the speakers a lot to prepare in advance some videos, to prepare in advance some presentations so that we can do it. No one can plug their computer. We are forced to use with the OBS system that is during the live transmission, so that we are forced to have that on one main computer. And I would like to thank all the authors, all the speakers that played the game, and it was really nice that we could set it up and have this hybrid mode. So thank you very much. I want to applaud you. So we have the collocated Wicked workshop, which will take place on Thursday. The program was set after we opened the registration for the conference. So some of you didn't register at the same time to the Wicked workshop. It is still time to register. There's still some space in the room, obviously, and so don't hesitate to go and visit the page and have this extra registration for Thursday. It will help also the workshop to be alive, and there's going to be very interesting. There are going to be very interesting presentations. So don't hesitate to look at the program and register if you want to attend this workshop. We've tried to get inspired by what Werner did last year. It was easier because it was online, so you could set it up online, but maybe we want to try it. So we're going to try to have the best fast-forward prize from the public, the best poster prize from the public, and the best presentation prize from the public. So there's at least 2 links that we've prepared for the best fast-forward and the best poster. So check which one you like, and then once you receive the link, you will be able to vote for those. And we will giving the results at the closing ceremony. So for the city tour, there are many monuments in Reims. Reims is a historical city for France. This is the city where all kings were crowned. Not all, but most of the kings were crowned, and you can know more about it if you're visiting these monuments. So I would advise you to go and visit the Saint-Remy Abbey and the cathedral as well of Reims. And do as much as champagne tour as you can do, because the cellars are absolutely fantastic. You can't imagine we are actually above some gallery, and the champagne wine is spread everywhere under our feet. So it's massive, and you will really enjoy it. There are also the Tau Palace, which is next to the cathedral. But you will have a chance to visit it if you participate to the special event on Wednesday evening. So tonight we will go to the City Hall of Reims. So you should have on your ticket there's the address. We will try to have groups of people to go there. The organizers, we came by car this morning, so I'm not sure we will be able to bring you there. I hope that there's going to be some forming groups to go there. But it's not far. You can see on the map. From here, it's a 15-minute walk, so you can reach there very easily. So it's going to be a welcome reception, so it's not going to be a dinner. You're going to have some small bites and drinks, and a welcome from the city representative and the president of our university. On Wednesday, there's a woman lunch, and it's an exclusive event for women. We're sorry for that, but we need to identify ourselves because we're still much underrepresented than men in this conference. And it's going to be at the Demeure des Comtes de Champagne, which is close to the Hôtel de Ville, to the City Hall. And it's also accessible at a walking distance. And this event is sponsored by Disney Research and the Tétinger Champagne House. And then on Wednesday evening, there's a special event at the Palais du Tau. So the Palais du Tau touches the cathedral. So if you find the cathedral, then you find the Palais du Tau. It's very easy to find. So we're going to have a dinner within the museum, which is the Palais du Tau is now a museum. And they welcome us from 6:30. On Wednesday, there's going to also be the General Assembly of the Eurographics Association. So those who are not members and do not want to follow this General Assembly, you can start to go and visit the Palais du Tau from 6:30. And others, we will be able to join right after the General Assembly and visit the museum. We can stroll inside the museum, just us. It's a private reservation just for us. And then we will have a seated dinner. You have on your tickets as well, you have a ticket with the login and password for the Wi-Fi. Those who have EduRoom, you can directly use EduRoom for the Wi-Fi. The Wi-Fi is installed only in the used space for the conference. So you have it only in the rooms and the areas where we have the posters. You won't be able to have the Wi-Fi elsewhere. So some people told me this morning, and yes, it is. If you are at the entrance, you don't have the Wi-Fi and etc. So it's only located in the main places. This is the numbers I got. We have above 300 participants on site. Some of them actually are registered on site but attend remotely. So I think we're more around 300 present at the conference. These are the numbers from first day. I compiled them first day for the presentation, so they might have moved a little. I know there have been some registration. And I'm sorry to say, but if you hear French in the corridors, this is normal. We're quite a big number of French representatives. It's 149 that I have on this on this diagram, and then there's Germany, who is following. It's not so far actually, Germany from Reims, so I guess it helped. But there's also a big graphics community, so 35, and then Austria, USA, Switzerland, and Israel, and many others. So we're very glad to have so many countries that publish and attend and speak at the conference. So yeah, maybe I should say there's almost 100 remote participants as well that are following the conference from remotely. So thank you very much. I hope I didn't forget anything, but I think I spoke already for quite a bit. So if you need anything, please come to us, and otherwise enjoy the conference. Thank you. So now there's Jean-Michel Dischler, the president of Eurographics, who will...
The association. So this year I'm really particularly pleased to welcome you in person here in Reims in France. This year because after 2 years in which the conference could only take place online, it's really a great pleasure and a honor for me to see you in live and not only behind a screen at home or in your living room. So first of all, of course, I would like to thank the organizers for their really great work, because as Céline told, it was certainly really not easy to organize this conference, because it's for the first time it's a hybrid conference, so face-to-face and online, and this is really the first time. So this allows us here, the association, to welcome you not only online, on screen, but also really here in front of you. And organizing this hybrid format has surely been really a great challenge. And so I would like to warmly congratulate the organizers for having mastered this, and really quite well as far as I can see here. So thanks to the tremendous efforts, thanks to your tremendous efforts, we can enjoy being here today in this auditorium, and also for many other peoples, 100 you said, behind the screens, and really for that we would like to thank you. So let me just say, it would not take a long time, just a few words about the organization. I would like to emphasize that the association, in spite of these really great difficulties of the past 2 years, has managed not only to maintain its 2 flagship conferences, which are this conference, Eurographics, but also Euroviz, at a really high level of quality. And of course, the same applies for all other workshops and symposia that the association is organizing. And really, it has also been able, in addition, to adapt and to evolve. And this is thanks to the support of its individual and institutional members. The association exists because it has members and volunteers. And these members are the researchers and research institutions in the field of computer graphics. And therefore, I would like to appeal to you to continue to support Eurographics as you have done so far. Eurographics is not limited to these highly visible international conferences. It also serves to promote our discipline to our national decision holders and to make it visible, showing presence, showing that computer graphics exists as a scientific discipline is important, especially in these times. And in addition, Eurographics events also serve as a career booster precisely for younger researchers and for the future, and for whom a publication at one of these conferences that is organized by the association can have sometimes really an important impact on their careers. And it makes careers visible through its prestigious awards that we will see right now given by Roberto, which will be the next speaker, I guess, and which recognizes exceptional talents. Through its digital bookstores and publications, the organization makes also scientific material available and accessible to all. And all these services are only possible thanks to the support of its members and volunteers. And in order to maintain these services in future, I really ask you to renew your membership at the end of the year and to encourage colleagues who are not yet members to become members of the association, to show that they belong to this computer graphics community. And by the way, I would also like to invite you, at least all members, to participate to the General Assembly that will take place on Wednesday. It's important. It shows also that when you are a member, you are an actor. You can help in taking decisions. So that's all I wanted to say for the association. So thank you again for your participation. Thank you to the organizers. Thank you to the authors. Thank you to the members of all these program committees. Thank you to all participants here on site remotely. And I hope, and no, I do not hope, I'm sure we will enjoy this 2022 edition of the Eurographics Conference. Thank you very much. Thank you so much.
So now we're going to have a presentation from the... do you want to go first? Oh, I was thinking the paper chairs, maybe? Yeah. Sorry.
So thank you, Céline, for the introduction. It is our pleasure to present you this unforgettable experience of chairing the full papers program. We are very proud of the exciting programs that we managed to set up during all this year, thanks to your numerous submissions and that you will experience during all that week. That year, we had 119 full paper submissions, which is rather similar to last year with a small decrease. And among those papers, 40 papers were accepted, which gives a 33.61% acceptance rate, which is lower than last year. However, this year we had 11 papers who needed major revisions and who could be submitted as a in a fast-track mode to CGF. And additionally, there will be 9 CGF papers that will be presented within the conference, within the full papers program. So we had submissions from all over the world, and more specifically, the countries with the highest numbers of submissions were China, France, United States, and Germany. And if you look at the accepted papers, they cover Europe, China, United States, but also Israel, Switzerland, and United Kingdom. Most papers usually have between 2 and 5 participants, with a targeted contribution that should be replicable by interested users. And if you look at the topics that were preferential that years among the submissions, you can see that there was mainly there was a lot of papers on animation, followed by papers on methods and applications, and imaging and video. There was already that trend was already present last year, and if you look more precisely, you can see that it's very difficult to have a paper in modeling, but also in animation. It's quite more difficult than in the other topics.
So let me try to explain to you the reviewing process here. So first of all, after the deadline, so once the people submit their papers, so we began the bidding, which is done by IPC members. And then based on the bidding grade and also the expertise of the ICP members, we start sorting. So sorting is done by advisory board, and then once we have, so we actually have a full list of the IPC members assigned to some certain number of papers. So, and for the reviewing process, we have, so our goal is to set at least 5 papers for each submission. So we have a primary and a secondary reviewer. It's like a C-graph. So then we have some primary reviewers to assign the 2 tertiary reviewers, and also secondary reviewer also assigned 1 tertiary reviewer. So in total, we're going to have 5 reviewers. And I'm very proud to say that all the submission in this years, we have at least 5 reviews. So, and then once we finish the whole review, so we begin with the rebuttal process, and the rebuttal process is basically allow the authors to address some certain error in the review. And then after this, so we begin with the tertiary discussions using BBS, so which involved with the IPC members and also tertiary reviewers too. And the last stage, so we have a virtual IPC meeting, and then IPC members actually went through the submission and the review and also rebuttal and the discussion, etc. And then finally, they end up with choosing 40 full papers this year. Right. So actually, I would like to thank many people here. So first of all, let me begin with the advisory board. So Theodore and Rachel and Sylvain, Ivan, and Mikhail. So they helped for paper sorting, and also I would like to thank their patience in replying our emails even during weekend. Also, here we have a very big list. It's 65 IPC members in total. And I hope you can read all the names over here. So first of all, they are involved in the reviewing process, and also they also wrote review. And then finally, they invite some expert reviewers who are relevant to the submission. So, and when we invite IPC members, we follow the rule. It's no more than 3 consecutive years of IPC participations. Right? And then here we have an even bigger list. It's the name of tertiary reviewers is 299, is virtually 300 people are working on this review. You might get surprised, actually we have 600 review. Actually it's even more than 600. And to get the full paper list. And then without this help, it wouldn't be possible to have a wonderful full paper program this year.
Now, we have reached the opening of the conference, and it's time to thank the session chairs, who will ensure that the sessions run smoothly throughout the week. And the chairing will be done on site, but it will require many online communication with remote speakers that could not come due to travel restrictions. So it is a technical challenge that we will have to overcome, and we are deeply, deeply thankful to the session chairs for ensuring the success of the conference. We also want to thank the CGF editors-in-chief, the current one, but also the former ones, and namely Elvig, Benesh, and Pierre, for the publication of the full papers in a special series of Computer Graphics Forum. And we also want to thank them for providing us input to select a few CGF papers that could be presented at this conference to complete the program. And now we want, last but not least, we want to warmly thank Michael and Stephanie Benke for their invaluable support in the use of the online submission system, SRM, and also for preparing the final proceedings. We are not finished.
So actually there's a very last one thing I would like to share with you guys. So, well, we actually met, with each other online, of course, almost for 1 year, in order to prepare the full program. So I think we are exchanging so many emails and day and night. And also, I'm in Korea, and Raphael in France, and then we are in different time zones. We actually work as like one team. It's 24 hours and 7 days. It's a great, great pleasure to work together. And also, I would like to thank the EG General Chair, Celine. It's a really, really great job. And without her, we wouldn't make a very good program like today. And also, we would like to thank the EG executive members and also all the people, who made this event possible. And also, the last thing, I would like to thank to the technical team. So, as Celine mentioned before, it's so difficult to manage hybrid systems, right? Not only on-site, but also online presentation and also communication. So we would like to thank again, for the technical team. And then, so this is the very last statement I would like to say. So it's our great pleasure to be a technical paper chair with Raphael and me together. And I hope you enjoyed the full paper program this week.
Now we let the place to Roberto Scopigno.
Evening to everybody. I will have to present the Eurographics Award 2022 edition. Okay. So just a brief notes on the history of this award. We started to give awards in 2004, so it's still some years, and the first edition was in the occasion of the 25th anniversary of our association. The goal of the program is recognize, highlight, and promote computer graphics research in Europe. And so we try to find individuals who have significantly advanced the field of computer graphics. We usually give 3 technical awards: a Young Researcher Award, Outstanding Technical Contribution Award, Distinguished Career Award. This one is given every second year, plus the EG PhD Awards. There's an error in the slides, but nobody has noticed. The EG PhD Awards was chaired by Niloy Mitra, and since this year it's chaired by Pierre Alietz. Sorry for the typo in the slides. This year we have one Distinguished Career Award. It's one of the years in which we have complete set of prizes. One Outstanding, 2 Young Researcher, and 3D PhD Awards. I would like to thank the committees for their hard work. We discussed this morning in the Executive Committee meeting the possibility of disclosing the names of the people which are behind this selection, these decisions, because it's not just myself and Pierre. We have 2 committees who evaluate people and take the final decision, and we will publish the name also of these people since next year in order to give complete transparency on the process. So let me start the PhD awards. Pierre?
Hi, everyone. So the Eurographics PhD Awards the goal is to recognize the excellent thesis work in Europe, and it's also the opportunity to offer them the opportunity to publish the state-of-the-art section of the thesis as a state-of-the-art report in the Computer Graphics Forum journal. So I wanted to say that I formed a small committee that is kept secret. So we were 6 people, and we really enjoyed reading one of the best thesis work in Europe. So I think it's really a great pleasure to evaluate. It's not also easy because we had to make a selection. Okay, so the winners are, there is no particular order, okay, it's just 3 winners. First one is Mark Haberman for his strong technical contribution to real-time capture and synthesis of human performance. Is Mark in the room? Okay, Mark. Mark did his PhD at MPI Saarbrücken, advised by Christian Theobald. You need to go on to step up on the stage. I don't know if there is someone taking a photo. Yes, if there is one. Let's do that. Want to say a few words?
Well, I haven't prepared a speech, but thank you very much. It's a real honor here to be here today, and I hope you enjoy the conference. I'm also looking forward to the talks. Thank you.
Second PhD award is given to Ylva Ferstel for her pioneering new methods for generating virtual human gestures from speech. And Ylva is not attending the conference. She's remote, so she sent us a video. And Ilva did her PhD at the Trinity College Dublin, advised by Rachel McDonald. To click on that video. Should I? On the video, yeah.
Hi, I'm Ylva Festel, and I completed my PhD at Trinity College Dublin in Ireland under the supervision of Dr. Rachel McDonald. And I first joined Rachel's lab for an Erasmus internship and then stayed for a PhD in multimodal conversational behavior synthesis for avatars. And right away in that field, I gravitated towards the area of co-verbal gesture generation from speech. So in a nutshell, I was developing machine learning models that take as input some speech audio recordings and then produce as output the corresponding upper body movements for a virtual character. And this allows us to make virtual characters more engaging and lifelike without costly and unscalable animation. So I'm very honored to receive the Eurographics Thesis Award and want to thank the committee for taking the time to assess my work. And then my greatest thanks goes, of course, to my supervisor, Dr. Rachel McDonald, for all the opportunities that she gave me and for supporting me and encouraging me throughout. I also want to thank Dr. Michael Neff, who became a sort of secondary supervisor and was always very generous with his time and resources. So thanks to you all.
Third PhD award goes to Julien Philippe. Julien for his pioneering contributions to multi-view image editing and rendering, enabling casually captured scenes to be rendered with content alterations, such as object removal, relighting, or scene composition. And Julien did his PhD at INRIA, advised by George Dretakis. I think Julien is in the room. Of course not.
Yeah, thank you very much. I'm really honored by this, and I want to thank, obviously, George, who's here in the room. Yeah, I guess that's it. And I wear the same sweatshirt for consistency.
We are now to the technical awards. The first, First winner of the Young Researcher Awards is Angela Day, in recognition of her outstanding contribution to computer graphics with new approaches to reconstruct, semantically understand, and synthesize models of the real world. Angela Day's work is significantly advancing a thriving field of research at the intersection of computer graphics, computer vision, and artificial intelligence. Her work contributes to better ways to reconstruct, semantically understand, and synthesize models of the real world, which is of great relevance to computer graphics and augmented and virtual reality, but also for the design of intelligent systems that need to understand the world they interact with. The work of Angela Days is published in the top-tier conferences and journals in computer graphics and computer vision and has been widely cited. Eurographics is pleased to recognize Angela Day with the 2022 Young Researcher Award. Angela. Just the diploma, but you also have an heavy stuff for you. give me the diploma and this one, the lower one.
Okay. Thanks for the great honor to have awarded me this. So I wanted to mention, of course, actually, my first conference experience was in Eurographics in 2014. So thanks to Eurographics for helping me get my start into looking into 3D reconstruction, how to learn to reconstruct semantically informed 3D models of real-world environments from just commodity sensor kind of inputs. So thanks for the awesome experience here first in terms of computer graphics and learning about the 3D reconstructions. I also wanted to thank my advisor, Pat Hanrahan, as well as some key mentors, Tom von Kauser, Leo Giebes, Matthias Niesner, and also Rüdiger Westermann, as well as the amazing students in my lab now at TU Munich. So thanks.
Congratulations again. Second Young Researcher Award is Jürgen Bernhard. Jürgen Bernhard receives the Eurographics Young Researcher Award 2022. Jürgen obtained his PhD in computer science from Technical University of Darmstadt. He is now an assistant professor at the University of Zurich, where he leads the Interactive Visual Data Analytics group. Jürgen has already made groundbreaking and impactful research on a range of fundamental aspects such as the characterization, design, and evaluation of visual interactive interfaces that combine the strengths of both humans and algorithms. His novel work on interactive machine learning and data science application has paved the way for new exciting research and applications. For his outstanding and multifaceted contribution to the visualization and visual analytics community, Eurographics is pleased to recognize Jürgen Bernhard with the Eurographics Young Researcher Award 2022. Unfortunately, this year we have two persons. Jürgen is the first one who got ill in the last few days. So they had planned to be here. They spent money in planes and registration, and at the end, it was impossible for them to attend. So with great they were not so happy of that because obviously it's a nice moment to be there.
Dear colleagues and friends, thank you so much. I'm incredibly happy about this award. Unfortunately, I got sick over the weekend, so that I did have to cancel my trip to Raw. I'm incredibly sorry that I can't experience this moment
It's okay.
together.
Stop it. You start it again. Just can we try to start again, or?
It's just so sad. Nevertheless, I would use my short speaking time to sort of get in touch with a few people who brought me that far. First of all, I would like to thank Dieter Fellner and Tobias Schreck for our incredible works on visual search and data exploration techniques, especially for digital libraries in those days. Thanks for collaborating with me for more than 10 years now. I want to thank Jörn Kohlhammer for our applied collaborative research, especially in the sense of visual computing in medicine and healthcare. Thanks for collaborating with me with over 50 research papers right now. Wow. I want to thank Heidi Schumann and Cedric Vich for our joint projects in visual analytics on time series data. You have always been true mentors for me. Thank you so much. Dear Michael Sedelmeier and Matthias Zeppelzauer, thanks for our achievements in interactive visual data labeling methods. I'm sure that also in future we will be able to sort of shape the landscape in data labeling, solve problems of real-world users, and make methodological contributions to interactive machine learning. Finally, I would like to thank Tamara Mansner for our collaborative design studies and contributions on methodology and visualization design. It was just fantastic to be together with you at the University of British Columbia in Vancouver. Greetings to all of you from the University of Zurich at the Lake Zurich. Enjoy your work, and once again, I'm so sorry that I can't be with you. Thank you very, very much. Have a nice time. Bye.
Big applause for this colleague who is probably looking at us from his house now. Could you switch? Okay. So we are now at the Outstanding Technical Contribution Award, and the winner is Diego Gutierrez. Diego Gutierrez is a professor at the Universidad de Zaragoza in Spain, where he founded and leads the Graphics and Imaging Lab. His main areas of interest include global illumination, physically based simulation of light transport, virtual reality, computational imaging, and perception in computer graphics. Diego has made outstanding contribution to several research areas of core relevance to computer graphics. His work is distinguished by his deep interest in pushing the boundaries in simulating light transport, for example, by including the time dimension or targeting novel display technology, and his quest to understand how state-of-the-art computer graphics techniques relate to human perception. In addition to this technical contribution, Diego is highly respected for his success in fostering thriving research communities. This includes not only his leadership of the Graphics and Imaging Lab at the University of Zaragoza, but also its service to the broader community with milestone contribution to journals and conference management. In summary, Diego is a role model in the field by showing a breadth of research topics while maintaining a deep technical focus and making pioneering contribution to many areas, and by inspiring young researchers to continue pushing forward the state-of-the-art in computer graphics. Eurographics is pleased to recognize Diego Gutierrez with the 2022 Outstanding Technical Contribution Award. And as you can imagine, this is the second person who got here and sent us a video to thank and to say hello to the community who gave him the award. This should start. Perfect.
Well, thank you very much. I'm honored to receive this award from Eurographics. Unfortunately, I cannot be there today because I hurt my back and I cannot travel. So video it is. Of course, any award, even individual awards, are never due to the effort of one single person. So I would like to thank, starting with my PhD supervisor, Francisco Cerón, who introduced me to graphics as an undergrad. Of course, all my colleagues, co-authors, and students, and I would like to highlight a few names that helped me early in my career, like Holly Brushmeyer. The first time that I worked in graphics, I was trying to reproduce Holly's tone reproduction papers. And this was before email, that's how old I am. So there was no email, and I, of course, had doubts about the papers. So I would write her handwrite letters with stamps and everything, with my doubts, my concerns about the paper, send them to her, and just wait. And a few weeks later, she would actually answer me by letter. And she was very nice. And she would actually say, why don't you use email the next time? But I had no email in my university, so I would write her again. And yeah, thinking back in those times, I really appreciate that Holly Brushmeyer took the time to answer me by letter. Also, Alan Chalmers and Eric Reinhardt, they encouraged me also early on in my career to pursue this career. They saw a presentation that I made in 2004 and said, hey, maybe you can be an academic at some point. And I had never thought about it at that point. And also Henrik Van Jensen and Ramesh Raskar, who very kindly allowed me to visit them and work with them in San Diego and at MIT, and from whom I learned a lot of things. Of course, I want to thank all the reviewers that rejected all our earlier papers. Yeah, maybe not all of them, not all of the reviewers, but you learn a lot by rejection, right? So this was not an easy ride. To build a successful group was not easy. It took a lot of rejections, but we learned from them. We learned how to write, how to do better research. So thank you, reviewers, for your time and your rejections. Also, thank you, Eurographics, of course, for this award, for picking me out. There's a bunch of people that deserve this at least as much as I do. So thank you for choosing me. And of course, thank you to my family and my friends for basically always being there. But the one thing that I'm the most proud of through my career is having built the graphics and imaging lab in Zaragoza. As I said, this has not been easy. This has required the effort of many people, lab members, past and present. So all of you guys, this award is mine as much as it's yours. Thank you very much. And to all of you in the audience, again, thank you very much.
I also hope that Diego is looking to the presentation and so it's enjoying it with us. And we have nearly finished. We've just missed the last one, the Distinguished Career Award. I'm very pleased also because this year I can present this award in her native country since we are in France. The awardee is Marie-Paule Cany. Marie-Paule Cany don't think that organizing the Eurographic conference in your country is sufficient to get the award, obviously. But in any case, it's a pleasure. At least she has a lot of colleagues in the room, as we heard before. Marie-Paule Cany is a professor of computer science at the École Polytechnique, where she leads the Modeling, Simulation and Learning Group. Her research interests include shape modeling and computer animation, where she has made multiple pioneering contributions. From implicit surfaces to the animation of deformable bodies, Marie-Paule has proposed impactful models for representing shape and motion. She introduced novel ideas for modeling and animation of hair and garments, as well as natural phenomena, from lava flows to ocean waves to clouds. She is one of the pioneers of sketch-based modeling applied to a variety of shapes such as garments, trees, and developable surfaces. The contribution of Marie-Paule to research, management, and community building are also outstanding. She served on multiple leading roles in the computer graphics community. She was the president of Eurographic Association and was the director at large in the executive committee of ACM SIGGRAPH. Cany served as a technical paper chair of SIGGRAPH 2017 and of many Eurographics events. Marie-Paule has also received several prestigious awards, including the Eurographics Outstanding Technical Contribution Award in 2011. She was elected for the Accademia Europea in 2013, for the HM SIGGRAPH Academy in 2019, and for the French Academy of Science in 2020. Our mind is boundless in its ability to visualize and design. Her work has created conduits for communicated visual ideas used by a generation of researchers and practitioners. Thus, her research has enabled collaboration between creators, scientists, and engineers and significantly advanced the field of computer graphics. Eurographics is pleased to recognize Marie-Paule Cany with the 2022 Distinguished Career Award. Marie-Paule? This is for you. For you?
Yeah. Thank you very much. Thank you very much. So I'm so pleased to receive this, to be granted this recognition by the Eurographics Association, which has been so dear to me for many years. In fact, my first Eurographics conference was in Vienna 31 years ago. And since then, I was in this Eurographics community. I was already assistant professor in Paris. From Paris, I moved to Grenoble. And then 5 years ago, I moved back to Paris. So the people I would like to thank are, first of all, my family, and especially my 3 children, who was so supportive for all these years when I was working so hard on research. The second group of people I would like to thank I put some of the faces here, but of course I could not fit anybody, everybody. But the people who shared team with me, in France is very particular because we are not a professor alone with their student, but we are sharing teams, we are sharing projects, budget, and very often co-advising students. And all those people here on the right, starting with my PhD advisor, Claude Puech, on top. So we built team together. And we worked together for many years. We tried to get funding, we tried to set up projects, and these colleagues were so supportive. It's really thanks to them that I could do this career and manage to have those contributions. And there is a second group of colleagues who I would like to thank, is all of you who worked with me, who collaborated with me, who co-advised students with me. And here I have put a few of the faces of the colleagues who are the most relevant and inspiring to my career. Maybe some of them inspire me with the way they are taking research and supervising students. Others were really key helpers and collaborators at key moments of my career. And I'm particularly happy to have some of them who are still willing to work with me. And at this stage of my career, when I'm president of department and have so little time for research, I still have some colleagues who ask me to have colleagues, to share PhD students with them, to have some application for project with them, and this is so nice. And of course, most of my career was the work I did with my PhD student. And here it's the most enjoyable time I could have. We spent really great moments co-inventing many different stuff. In fact, I supervised 36 PhD students, plus master students, plus a few postdocs. So I decided not to put a long list of names, but rather to give some examples of the research we did together. And really, I hope that everybody here in the room will have such opportunity to work together, to co-invent things with colleagues, students with their advisors, and it's really what makes research for me. Thank you very much.
This closes the session. I want just to remember you something which is really important. You should help us. You should help us. It's really important to receive nomination of clever people, so don't be shy. Send us nomination for the next year event, both to me and to Pierre, in order to simplify our work. If we start from a good number of names nominated by colleagues, our work is easier and it's also much easier not to make errors. So thanks a lot, and remember to send us nominations.
So thank you, Roberto. Thank you, Pierre, and congratulations to the awardees. We're running late, so I'm going to ask all the fast forward to be ready to jump on the stage when it's their moment. And we're going to start right now the fast forward. And right after the fast forward, we're going to go to the City Hall where we are expected at 7:30. Thank you.
Hello everyone, in this work we present a fast ray tracing framework for skeleton-based implicit surfaces. We start with a dynamic screen space accelerations, and then iteratively fit low-degree polynomials to find fast and efficient ray surface intersections so that we are able to smoothly render these shapes and including complex microstructures. Our talk is tomorrow. I hope to see you there. Thank you.
We present Dressy, a hardware-agnostic differentiable renderer with reactive shader packing and soft rasterization. Dressy can perform inverse rendering to optimize 3D geometry by 2D images. Dressy can run on various devices, including a laptop and mobile. Our full-AD system design eliminated hardware dependency and obtains higher performance by separating DR algorithm and differentiable functions. Balkan API and automatic differentiation for DR are key factors. Dressy is high performance. It is 2 times faster than previous methods. Dressy is robust and accurate in mesh optimization. Complex shaders are also supported in forward and backward passes. Please come to our presentation.
The title of our paper is Real-Time Virtual Try-On from a Single Example Image to Deep Inverse Graphic and Learn Differentiable Renderer. The contribution of our paper are the following. We propose a self-supervised framework for learning an inverse graphic encoder for non-differentiable rendering engine. We applied this framework to the task of example-based virtual try-on for makeup and hair color, reaching state-of-the-art results in real time on mobile devices. To the right, you can see sample results generated by our method.
Program traces are animated values evaluated during program execution. We propose a compiler framework that automatically extracts program traces for pixel shader programs. Each trace can be viewed as a feature map that is used to augment learning tasks which traditionally takes RGB input. For example, denoise output shown below based on the noisy input shown above. Or reconstructing a complex shader shown below based on a simplified input shown above. Or predicting the output of a flocking simulation based on the one with coarser time steps.
I want to enlarge the lighthouse in this photo, but zooming in and cropping would cut out the foreground ridge, an important compositional element. Using Zoom Shop, we can enlarge the lighthouse while keeping the ridge in place. In Zoom Shop, users can select different depth regions and adjust their scales independently. Zoom Shop uses a nonlinear camera model and a depth-aware warp to maintain important structures. We can adjust object scale, foreshortening, and positions to edit photographic composition. Come to our talk to learn more.
Everyone, it's my honor to introduce our work. In our work, we design a future contrast masking loss and a depth mu law to make it possible for self-supervised tone mapping. This figure shows our whole pipeline. Here we show the visualization of the future contrast masking. The input is the future map from VGG19. We can see after processing, small contrast will be promoted and more details appears. The testing results also show superiority of our methods than others.
We present a new formalism for modeling terrains using gradients. A terrain can be easily authored by combining a guiding gradient field and hard altitude constraints. This gives rise to a wide range of authoring tools that allow the creation of canyons, cliffs, mountain ranges, and can be used seamlessly in a standard copy and paste formalism. It is even possible to author a mountain that looks like the EG logo in a few user strokes. If you want to know more, come to our talk on Tuesday at 11.
Discrete Chebyshev nets are quad meshes with all edges of equal length. They are widely used in many fields.
How can I get such meshes?
Discrete Chebyshev nets can be generated by triangle meshes.
Then how can I edit a discrete Chebyshev net interactively? Can I deform the origin triangle mesh and regenerate a new one?
In such way the singularities may change a lot. Our article provides a way to deform discrete Chebyshev nets directly by constraining edge lengths and solving an optimization problem.
Reliable estimation of facial landmark positions is still an active research field, but the layouts in use remain purely empirical. Layouts generated by previous work lack similarity, and the question of what is a good layout remains open. We suggest to derive landmark layouts from blend shape models. In our approach, we assume that at least one good landmark is required for each blend shape. In addition, we formulate the entire problem as an integer optimization that can be solved in blend assessment, even for higher values. Layouts computed by our method are similar, but more compact than empirical layouts.
How many different characters can you spot here? What if the answer is only one? State-of-the-art vision algorithms fail on animation as style changes drastically. We present a new style-adaptive representation learning algorithm using self-supervision. We leverage multi-object tracking to refine the base embeddings by a simple yet effective trick applicable to any video. Check out our work tomorrow at 4 p.m.
Do you want to do this cool bullet effect stuff for yourself? Well, setting up a camera array is just too expensive. Or you may just be too shy to ask someone to film around you. Now, just bring over your phone and a tripod. We have had a solution for you with this easy setup. Wanna know how we model the human body with a single stationary camera? Come to our talk.
Inverse rendering techniques for facial appearance capture often make simplifying assumptions. First, the lighting is assumed to be distant, resulting in incorrect shadows. We instead accurately calibrate the 3D positions of the lights. Second, cross-polarized images are assumed to have no specular signal, which is not the case for a multi-view setup. We model polarization explicitly to improve rendering accuracy. Third, indirect light bounces are often ignored, leading to overshoot and diffuse albedos. We propose a texture space technique to alleviate this issue. Come to our talk to see how we improve facial appearance capture methods.
Are you tired of grabbing beers from the fridge yourself? Why not build a robot to perform that task? We did not build such a robot, but our research regarding monocular depth estimation architectures indicates that there is a trade-off between the estimate quality of transparent objects and high-level scene details between different neural network architectures, with potentially horrible consequences for your beer-serving robot. For more information, join our presentation on fitness of general-purpose monocular depth estimation architectures for transparent structures on the first session this Tuesday in room 3.
Perfect set displacement mapping with CoMaps is great, but it takes too long to generate CoMaps. We introduce a quick GPO solution based on maximum minmaps. You can even compute CoMaps per frame up to 4K resolution. See you on Tuesday.
Global illumination rendering requires random light path samples. There are different techniques, for example, BRDF sampling and light source sampling, each with its own merits and drawbacks. Multiple important sampling combines sampling methods preserving their advantages. This paper addresses the problem of the optimal allocation of the sample budgets to individual approaches. Should you be interested, come to the Rendering and Illumination short paper session tomorrow.
Volume rendering is essential to improve image quality, and with many light sources, tree-based light sampling is often used. However, it's sometimes hard to maintain. Then, with the stochastic light culling, we can bound the light range for each light without any bias and reject some lights for shading. In this research, we propose an efficient method to extend it to volume rendering. Our method doesn't require any acceleration structure. If you want to know the detail, please come to our talk. Thank you.
You know, real-time path tracing is becoming more and more a reality every day, but still high noise level of renders make it hard to rely on real-time ray tracing even with denoisers. That's why I'm planning to present a new screen space path guiding technique which decreases the variance of Monte Carlo estimator and also slightly improve the overall performance of computation. See you on Tuesday at 11 a.m.
.3D printing objects with overhangs often requires disposable support structures that are removed after fabrication. This removal step leaves scars where the supports meet the object, so they should touch in as few places as possible. We propose a new method for generating bridges and pillar supports inspired by example-based model synthesis. We take into account the object geometry to minimize the number of contact points, facilitating removal and cleanup. Contrary to standard synthesis algorithms, this is done without any backtracking or trial and error.
We present a way of generating textual descriptions as extension of scene layout synthesis. As example, we generate scenes of medieval fantasy villages. Automated descriptions could be used to make 3D content more accessible or allow generated actors to describe the world surrounding them. In our proof of concept system, first a scene relationship graph is derived from a hand-tuned graph grammar, then scene and text are produced using a combination of established techniques. Results are evaluated in a pilot user study.
Again, in this paper, we transparently render and slice skeleton-based implicit surfaces. For this, we propose a precise per primitive interval arithmetic so that we are able to transparently render and slice these surfaces robustly and efficiently. Our talk is tomorrow. I hope to see you there. Thank you.
Present materia. Starting from a single picture taken in the wild, it removes the shadows, recovers the surface normal, the material roughness, and the geometry to produce a high-resolution material. Now you have 20 seconds to produce 4 realistic materials to texture this 2D scene. Let's go in the wild. Thanks to 2 cascading neural networks, Materia allows to capture outdoor materials under natural lighting with any camera device and works at high resolution. Come see our talk Wednesday morning.
Have you ever wanted an Instagram full of motivational early morning sunrise shots, but you're too lazy to get out of bed that early? We present a method for single image relighting of outdoor scenes under arbitrary sun positions, including those early morning sunrises. We achieve this by utilizing an off-the-shelf depth estimator to get noisy scene geometry. Given a sun position, we sample across the depth image along rays towards the light source. This allows us to create a 3D feature volume which is passed into a 3D convnet to produce accurate shadow maps capable of long-range car shadows.
Imagine you would like to change the appearance on some of the objects in this image, like making the lamp up there look less glossy. Well, usually you would need to have some 3D definition of the scene and know how to manipulate the material in it, and usually you don't have a 3D scene. Well, good news, you don't need it anymore. Our method allows to take just a picture of an object, set an intuitive target appearance, and it will change the image for you. Our method is based on deep neural network trained with crowdsourced perceptual data. Yes, we have all of that. So I hope that all these buzzwords will convince to come to your talk.
You don't know which crowd simulation algorithm to use? Tired of checking which one works best? Stuck using a super complex algorithm just in case? Come to a presentation Wednesday morning. We systematically studied algorithms and parameter values in various contexts, and we mapped them to the best performing ones. The explanation of the evaluation and the context are included in the presentation. But wait, there's more. We will explain how characters can adapt their motion strategy to changes in the context, mid-simulation, and independently. Don't miss the chance to join us on Salon on Wednesday.
Generalizing motorcycle graphs to the volumetric setting, we present the motorcycle complex, a non-conforming partition of a volume into cuboidal blocks. The partition is constructed by extending walls, starting at singular edges and stopping only once they hit the boundary or another wall. Compared to conforming volume partitions like the base complex, it is coarser and thus faster to compute by orders of magnitude. On tetrahedral meshes, the motorcycle complex is a key ingredient for robust hex remeshing. Compared to previous state-of-the-art methods, it allows to generate much coarser meshes without defects.
We propose a simple yet effective method to perform surface remeshing with hard constraints. The challenges are twofold. First, continuous and discrete degrees of freedom. Second, non-differentiable constraints and objective functions.
How do you solve these problems?
We convert a constrained optimization problem into an unconstrained form and design a differential evolution algorithm to minimize it. We successfully apply our method to error-bounded Delaunay mesh simplification and error-bounded angle improvement. The time is up, let's talk about it next time.
We create volume meshes from point clouds and surfaces. Therefore, we fill up the volume with Voronoi cells, do a Lloyd relaxation, extract this edge graph, and in there we search for primitives which are constructed from a hexahedra by collapsing individual edges and are therefore at most hexahedral. And the final mesh consists of mostly hexahedral primitives, and the other ones are at most hexahedra but can be used as hexahedra, which is useful. See you.
Given a satellite top-down view image of your neighborhood, do you know the shape and composition of your roof? We present an automatic procedural modeling and deep learning-based approach to generate regularized building footprints and procedural roofs from a single satellite image. Our framework handles building footprint regularization, building decomposition, and roof ridge prediction altogether. Come to our procedural roof generation talk and see how the magic happens.
Human beings enjoy figurative art and can easily understand its content. Computers, on the other hand, have a much harder time understanding art, which would be surprising, as we consider them smart enough to drive cars. We present an approach for semantic segmentation of art paintings using domain adaptation between real photographs and a novel artistic dataset. Our approach learns the unique features of various art styles and combines this knowledge to achieve state-of-the-art results on seen and unseen art styles alike.
Are you interested in real-time texture space shading, but unsure which texture space representation to choose for your application? Join our talk about meshlets and how to shade them on Wednesday 5 p.m. and we'll show you our new texture space shading method. We combine efficient modern mesh shaders with a pre-computed texture space mapping to achieve a simple and flexible texture space shading method suitable for a variety of applications. We outperform previous work in terms of image quality, runtime performance, and temporal upsampling capabilities for a fixed number of fragment shader invocations. Join our talk on Wednesday for more details and discussion.
Subdivision schemes allow you to refine a mesh that fits well in memory into a detailed one that looks good on screen. Our algorithm applies loop subdivision extremely fast, enabling full recomputation at each frame in real time on the GPU. This allows unprecedented applications like visualization during mesh editing. We achieve this by reformulating the refinement rule over the mesh half-edges and enabling per half-edge evaluation in parallel. Want to know more? Come listen to our talk.
Just like marching cubes, dual marching cubes methods reconstruct surfaces from volumetric data which might come from CT or MRI. A major difference is that the result is quad only. However, in some cases we might get non-manifold edges. We show how these non-manifold edges can be removed in a simple post-processing step. It even works in complex scenarios with multiple incident non-manifold edges. Our CUDA implementation is available on GitHub and comes with a fancy GUI for you to test dual marching cubes and our post-processing.
Software tessellation on the GPU, developed by Curie and colleagues in 2019, looks something like this. Whoop, 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 whoop. Ah, stop it, you! Get over here! Now, no more jumping around. Get into the grid. To see how software tessellation with grids can make your GPU happy, come see us on Wednesday in SAL 3.
Geometry rendering sparse voxel trees can be equipped with a level of detail structure to reduce aliasing effects and noise during camera movement. However, the correctness of geometry rendered at lower levels of detail depends on the direction it is viewed from. So we propose a novel encoder-decoder neural network architecture that derives view-dependent supersampling patterns to resolve wrongly shaded pixels due to level of detail. Since the network is trained on local geometry patches, it generalizes to arbitrary models and it is able to resolve errors that cannot be detected by screen-based supersampling approaches. Thank you.
We compress character motion using a neural network while preserving its content. We train a neural network so that it predicts from time to the character pose. We propose adaptive Fourier feature to reconstruct complex motions. As a result, our methods can compress motions with rich details like this. Our talk will be Wednesday, 11, so see you at the talk.
We introduce Neural MLS, a space-based deformation technique guided by a set of displaced control points. Neural MLS is built upon moving least squares, where the control point weighting function, which is traditionally based on inverse distance heuristics, is replaced with a neural network. By training a neural network, we can inject the underlying shape geometry into the deformation parameters and exploit the innate smoothness of neural networks. Come to our talk to hear more.
We present a novel interactive facial animation editing system that can express the naturalness of non-linear facial movements in real time. The proposed system is based on a fully automatic algorithm that maintains all positional constraints while deforming the facial mesh as realistic as possible. If you are interested in editing facial animation, please come to our talk. Thank you.
Recent work has proposed a domain decomposition approach for breaking down complex readability simulations with contact into smaller partitions that may be solved in parallel. The approach reduces wall clock simulation time without sacrificing accuracy. However, for unstructured simulations, bodies frequently form and break contacts. Therefore, an efficient algorithm must be used to traverse a constraint graph and decompose simulation into smaller contiguous systems. We evaluate several efficient graph partitioning algorithms and even propose a new partitioning algorithm that outperforms the algorithm proposed in the previous work. Tired of blue zoom meetings or masks? Come and enjoy our colorful videos.
Are you tired of being two floating hands in virtual reality? We present a fast and easy to set up system to have accurate full body avatars in any virtual reality application. The user does a simple calibration step and the system handles the rest. Our avatars have accurate movements, time adjustment to the controllers, multiple mesh support, and collaboration.
We drop a ball on a wet sponge. The ball collides with and presses the sponge. With the pores compressed, fluid is ejected. For this, rigid body, elastic body, and fluid simulation must interact. We show how to mediate forces between the simulations, handling collisions, pore suction, and drag in real time. Come and hear the ultimate short paper talk.
If you were to edit a procedural model, you would need to tweak a set of sliders. It's too complicated and not cool. The alternative is to directly change the resulting 3D geometry, but you would lose the procedural representation. We present our paper about interactive editing of procedural models directly in the viewport. What you can see on the screen is an interactive editing session. Come listen to us on Thursday morning at 9 a.m. And yes, it's after the gala dinner.
Basically, our method is to create vector images using less dense meshes. Here's a nice example. On the left is a pair that we want. In the middle is the mesh created by our method. On the right is the mesh created by traditional method. Apparently, the mesh of traditional method is much more dense than that of our method, right? So let's begin our story.
Do your MPM simulations have numerical fracture? You could use the total Lagrangian formulation. But then, large deformations are hard to achieve, which were possible with Eulerian formulations for MPM. We present a method that achieves the best of both worlds. Our method can simulate large deformations while completely eliminating numerical fracture. To learn more, please come to our talk.
I'm doing this on behalf of the authors. It's expensive to simulate detailed fluids over a very large domain. So what the paper proposes is to couple any 3D fluid simulation with a 2D wave propagation method that is called the equivalent sources method. And so this extends the 3D simulation over an arbitrarily large domain, and you can still zoom in and see all the great details.
Continuous collision detection is widely used in physical simulations. We explore CCD methods for triangle meshes whose vertices move along linear trajectories in a time step, and introduce the first exact root parity counter for CCD functions. Our method enables the efficient and robust simulation of closed meshes. Come to our talk for more details. On Thursday, 10 a.m.
For the 20th anniversary of pre-computed radiance transfer, we introduce neural PRT. But what do a real-time technique from 2002 and neural rendering have in common? Our paper shows that there are many surprising links. If you'd like to find out how to get the most out of your neural renderer using insights from PRT literature, come see our talk.
Thursday morning. Thanks.
Physically based rendering of a scene from multiple viewpoints can be time-consuming. So fortunately, pass-reuse method can be used to amortize the cost of tracing light paths. However, it remains unsolved for dense heterogeneous media. We hence address this problem with new path transformation and a novel variance reduction technique that overcome limitation of MIS. So our formulation reduces significantly the variance for rendering of multiple viewpoints at the same time. Come see us on Thursday morning.
Radiance field differentiation is a growing need for rendering in computer graphics. In our work, we derive an efficient differentiation algorithm to compute the gradient of the spherical harmonic basis function. We apply this to spatially differentiate the projection on spherical harmonics of the radiance field produced by spherical light. We demonstrate the usefulness of such differentiation for real-time rendering by computing the radiance field produced by spherical lights and its spatial gradient on the sparse grid. Then, using an Hermite interpolation, the radiance field could be accurately interpolated on 18 points into the grid. Come to our presentation to satisfy your curiosity about the differentiation of spherical harmonics and to see other applications in rendering.
In this work, learning spectral unions of partial deformable 3D shapes, we explore the properties of the Laplace-Beltrami spectra. It is known that it encodes information about the shape geometry. However, it is not clear whether it is possible to perform spectral operations between different shapes. We show that it is indeed possible, taking the problem to combine two shapes. We show how to recover the full combined extrinsic geometry from the spectral partialities, or that it is possible to localize the union region on a template from those partialities. Learn more in the full presentation.
In this work, we present a simple yet effective formulation called coverage axis for shape scalation. Inspired by that cover problem, our method inherently introduces a compact and expressive approximation of the medial axis transform. Different from previous methods, coverage axis considers the problem from a global view and is able to handle generalized input, such as point clouds and poor quality meshes. Please check out the report and paper for more details. Thank you.
To create vector graphics of raster line drawings, we propose a vectorization method. Our method makes the output more accurate and reliable. To do so, Our key observation is that the boundaries of the lines always provide reliable hints on similar line drawings that are difficult to distinguish using traditional thinning algorithms. Come to our talk and find out more.
Tractograms are a representation of the white matter architecture of the brain. They are composed of millions of 3D polylines. We propose a method to visualize in real time those billion segments, leveraging the latest mesh shader pipeline for an on-the-fly synthesis of the dataset based on a compressed representation, enabling interactions with massive tractograms. If you are interested by medical data, want to know more about the latest mesh shader pipeline, or even take some inspiration for your next fur rendering algorithm, come to our presentation.
We present Z2P, a fast neural technique for interactively visualizing raw point clouds as images. Z2P enables easy control of view direction, color, and light position, and produces surface visualizations instantly. Our solution doesn't require globally consistent normal orientation, and also avoids the issues of holes and overlaps encountered in traditional spotting techniques. Come to our talk to hear more.
We present a new framework for computing closed-space filling curves, namely cycles filling a surface. Without counting the initialization, the method is divided into two steps. The first one is the genetic algorithm optimizing Hamilton cycle in a given graph, decreasing, for example, the number of transitions between zones of different colors. The final step optimizes the geometry, including smoothness and even spacing. Additional objectives can be added, like anisotropy, and vector field alignment.
Did you know it's possible to fabricate surfaces flat that can automatically morph into a prescribed 3D geometry? Sounds like magic, but it's just physics. The fabrication technique is really simple. You just need to pre-stretch a piece of fabric and then use a 3D printer to deposit some plastic curves on it. When the fabric is released, it automatically pops into shape. Come see our talk on Friday morning to see how it's possible to find the optimal pattern to print to reproduce a given 3D surface.
Check out the boomerang we just designed. It's so perfect, and let's check it out in motion. Wow, so graceful. No worries, our method comes to the rescue. Our method can analyze the worst-case loads of assembly structure, suggest new parts for the user to add, and optimize the geometry to make the best boomerang ever. Come to our talk for more examples. Thank you.
Crowd simulation is about to get sketchy. Come and discover interaction field and directly sketch how you want people to behave towards you. Enter a world where the only limit is your own imagination. Designing new scenarios has never been that easy. Even a baby can do it. So come to our talk on Friday morning to discover interaction field.
Our method, spatial directional mixture models, learns a single, joint distribution of the incoming radiance over the entire scene. This results in the directional distribution varying smoothly as we move through space. Using the same framework, we are also able to represent spatially varying BSDFs and ultimately perform product sampling. To learn more about our method, come to the session on rendering tomorrow morning at 9 a.m.
Thank you to all the speakers and the great presentations. I'm afraid we have to hurry up. So I will see you all in the city hall of the city of Reims, and I hope you enjoyed the day. Thank you.
Thank you.